go from current slide. I'll turn on the projector. And let's go over just a couple of announcements. I don't think any of these are too urgent for you, but we'll see. Tonight, starting at 7 o'clock, but y'all can't go because you'll be here unless some of you are in it, okay? The Miss Lawson Gate State coronation will happen tonight at 7 o'clock, just next door at the Bessemer Civic Center, okay? So if any of you absolutely have to go, I guess you have to go. Is there somebody else? All right. And I guess Jose Mendez? Is that right? What do you go by? What do you go by?
Mendez, my last name.
Huh?
My last name.
Mendez?
Yeah.
Okay, you go with that? Okay. All right, so we're just missing Mark, unless that's Mark's stuff there, and then we.
Yeah, he's outside. He said he was having chest pains. So
Oh yeah.
Yeah, I asked him if you wanted me to get help, and he told me to come here and tell you he's out there.
Okay. He told me to tell you.
He told me to tell you
me.
he's sitting right there.
Okay. Yeah.
I asked him if he wanted help, and he said he was okay. He's like right on the stairs outside the house.
He's what?
He's on the steps outside the house.
Well, we've got perfect attendance. It's great to see. But we do have two new people here who weren't here to hear the stuff from last time. And one of them's heard it all, okay? But for Mendez, let me just go over a few things. If you go to Blackboard, this course in Blackboard, you won't find anything there. Okay, yeah. Well, you will. No, not there yet. I did get the syllabus updated, but then 2 dozen things else happened, and I didn't get it loaded at Blackboard. I'm going to try to do that tomorrow, if I can. Okay? We've got to do contracts tomorrow and all sorts of things, so I'll try to get that done if I can. All right. So, but when you go to Blackboard and I get it all loaded, when you go to home page in Blackboard for this course, there's a series of blue tabs on the left. Now, nothing's in them now, but in the first group, they're grouped at about 5 to 7 or 8 in a group. The first group, there's one that says something like course information, course and book information, or something like that. If you click on that, that's where your syllabus will be. It's not there yet, but it will be. As soon as I can get it loaded, like I said, I got it corrected. Okay, go down right under that one. It says instructor information. There I will put my locator card. I don't think I have that corrected yet, but I'll get it corrected and load that in there. Then go to the next group. In the next group, you'll find a tab that says handouts, PPTs, that's PowerPoints, and more, or something like that. Now, nothing's there yet, but I'm going to put all of your PowerPoints that I'm teaching from, this is from that, all the PowerPoints for all 6 chapters we're doing, And I will also put the research paper instructions. That'll probably be first, then the PowerPoints, and then I'll put the link to the YouTube videos. Now, once that gets there, you'll be able to see and hear what happened in class last time. Because I record everything. I'm recording right now, 5 minutes into the class. So I recorded the whole class last time, and that's all that we talked about, the syllabus, all that we talked about, the research paper. The static instructions will be there, but you'll be able to hear me talk about them. Okay? My locator card, I went over that. You know, I went over everything, including things that are not out there. Safety, okay, fire safety, weather safety, active shooter safety, every kind of safety we can think of. And then we got started on Chapter 1. And we got most of Chapter 1 covered. This is where we're beginning in Chapter 1. So you can go back and catch up everything that you may have missed last time. Okay? Now, any other things? Let me just say this. Okay. Today we're going to have class for 2.5 hours as scheduled. Then we'll have 2 hours for lab. The lab for this first chapter. Okay. I've got most of the materials over in the lab, but I couldn't set up because I didn't know if there was a biology class coming in there or not between when I had time to set it up and when we'll be actually going there. So when we go there, I'll have some setup to do, but I'll get y'all working on it while I'm setting up the rest of it. Okay. Then, I'm pretty sure we'll finish Chapter 1 today in this 2.5 hours. We'll get started in Chapter 2. That means on Tuesday of next week, we'll continue in Chapter 2. Then we'll stop after 2 hours and have the first lab in Chapter 2. And then you'll have the test for Chapter 1. I always do the labs, either the last or next to the last, and test the very last. That way, if you finish a lab early and we don't have a test, you can go on home. Or if you finish a lab and we do have a test, you can get started on the test. When you finish the test, you can go home. You don't have to sit around and wait for us to start back lecture again. So that's sort of how we operate. Any questions on anything? Okay. All right. Well, then let's go on and pick up where we left off last time. We're in Chapter 1, page 17, and one of the last slides we did was pseudoscience, and there's a little blurb at the top of page 17 on seeing what you can find out. Just a variety of things on pseudoscience, okay? That's only if you're interested in that. So let's talk about laws and principles. And I'll tell you right off the top, there's not a lot of difference, okay? Sometimes some people call one thing a law, someone else may call that same thing a principle, and vice versa, okay? So this is just a way to organize things, okay? So what are laws? Important relationships observed to occur time after time after time, okay? The law of gravity has never changed as far as we know, okay? You throw something up in the air, it's going to fall back. That's a law. Important relationships observed to occur time after time, okay? These are mostly descriptive in nature, okay? Now, they give an example of one. There was a guy, I can't think of his first name, last name was Charles, Charles's Law. It describes the relationship between temperature and pressure in gases, okay? If a gas is held at a constant volume, you have some fixed volume, it's not going to change, and you increase the temperature, the pressure is going to go up. Decrease the temperature, the pressure will go down, okay? So as long as the volume doesn't change, that's the relationship between temperature and pressure. Always will be that way. Now, this is a quite with this, but I did graduate work up in Nebraska. Pretty cold up there in the wintertime. And while I was up there, there was a lady that worked at our church who was divorced, and she had a young son getting into high school, and she just wanted, his dad lived across the state somewhere, so they didn't get to spend a lot of time with him. She wanted someone to spend time with. I said, look, I'm a bachelor, young, I don't know anything about kids, so I didn't think she was talking to me. But then the church had a softball team, and I went out for it, wasn't any good at it, but he did too, the young kid. And we just hit it off. And so I said, well, maybe I can spend some time with him and do some stuff, so I did. One time I went over about this time of year, maybe a little bit later, and he wanted to shoot some basketballs on the goal in his garage, but the night before, he left the basketball outside. So we went to pick up, and he said, oh no, it's flat. I said, well, put it in the house. So it was probably around 35, 40 degrees. I said, well, just put it in the house. What good is it? I said, just put it in the house. So we went on and did some other things. I said, well, you still want to shoot a bit later? He said, yeah. So we go get it. He said, well, it's flat. Well, I haven't pumped it up yet. I said, go get the ball. Went to get the ball, and there it was, right ready to go. Why? It left it out all night. The temperature had dropped. The pressure had dropped, okay? But then when you put it in the house, where it's probably 65, 70, something like that, then it went right back up. Charles's law happens every time, okay? Those are laws. Principles, on the other hand, also descriptive in nature, but usually more specific than laws. Now, isn't that weasel words, okay? How do you distinguish what's more specific or not yet? Okay. But anyway, principles, like I said, they can be either way. The difference is largely one of extent. And talk about a weasel word, what does that mean, okay? Here's the clue. Not always a clear distinction between what you call a principle and a law. An example, Archimedes' principle relating objects, fluids, and buoyancy. Some people would say that's a law, okay? Here they're saying it's a principle. An object displaces its weight of water unless it's heavier, denser than water, and then it displaces that volume of water. So that's Archimedes' principle. Now there's another, and we may run into it in this course, but I'll do it whether or not. This is called Bernoulli's principle. Now there was a whole big family of Bernoullis. There were two brothers, Johann and another one started with J. James maybe, Bernoullis. One was older, other was a little younger. I think the younger one thought he was smarter than the older one. They were both brilliant, okay? And they competed like cats and dogs, okay? But then either one or both of them had some kids, boys, okay? And they were brilliant, most of them, it seemed like. And one of them came up with this principle, but they competed like cats and dogs too, at least with their fathers. In fact, there was one story, whichever of the Bernoulli brothers was entering his contest that he won just about every year, beat his brother just about every year. And he entered it, and then the letter came to the house. He thought it's going to be, and they said, oh no, this is for Daniel, or whatever his son's name was. He said, what? And sure enough, his son had entered the contest, unbeknownst to the father, and beat his dad. So, of course, the dad kicked him out of the house, okay? He didn't want the competition. Okay. Here is Bernoulli's principle. This is one of the sons, the second generation. I'll ask you, what will happen if I blow under this piece of paper? Any guesses? Goes on. Sure enough, she's right. Okay. Have I done this in the other class? Okay. No. All right. What if I blow over the top of this piece of paper? What will it do? It goes up. Ah. Wait a minute. Why is that? Do you know why?
I don't know exactly what.
Okay. Guess what? Bernoulli's principle. Okay, I got it. But that's exactly it. Here's why. Of course, when you blow under it, you're forcing more air against it. That increases the pressure down here. And of course, blowing against the paper slows the blow down, so that pushes the paper up. Transfer of energy between the air and the paper pushes it up. What in the world makes the paper rise when you blow to the top? Here's Bernoulli's principle. The volume of a fluid, the velocity of a fluid is indirectly proportional to the pressure that it exerts. In other words, if you increase the velocity over the paper, like I do by blowing, then the pressure gets less, and that's what lifts the paper up. Now, let me just make a guess. Oh, I forgot to do the announcements today, didn't I? Started them, but didn't finish them. Volleyball team, I was using that. The volleyball team will be playing a tournament tomorrow and Saturday up in Gadsden, Alabama, the Gadsden State Tournament. So if you happen to be around Gadsden tomorrow, go by and cheer the volleyball team on the victory, okay? All right. And then next Monday evening, before we meet again, it's a home match versus, so it's on the Birmingham West campus. They're hosting Bevel State. So go by there to see them if you can. That'll be at 6 o'clock in the evening. Okay, sorry. That was a commercial break. Okay. So, Bernoulli's principle says if you increase the velocity, you decrease the pressure. I bet you most of you have experienced this. Any of you have a pickup truck or have ever had a pickup truck? Okay. You ever had anything on the back of your pickup truck, tooling down the highway at a pretty high rate of speed, and you see it leave the truck? Exactly. Bernoulli's principle, the increased velocity of the air over the top decreases the pressure, picks it up, and carries it away. Now, I've heard people say, oh, the air underneath pushes it up. No, well, it sort of does, but it's because the increased velocity across the top decreases the pressure.
Is that like what tornadoes do?
Yes, that's exactly what tornadoes do. Very good example. When you have a tornadic activity over a building, what is usually the main thing, the first thing destroyed? The roof is actually lifted off the house. Sometimes houses are lifted off the foundation because the speed of the air is so great, it actually lifts them. The shingles are lifted off, everything. Most of the time with a tornado, if it's strong enough, the windows are blown out. Now, if a limb comes flying in, then that brings the glass inside. That's why you get out of the way of it. But if it's just a pressure problem, the windows are always blown out. Because the increased velocity of the air decreases the pressure on the outside, increases on the inside. Ever been driving down the interstate or any road and a big old 16-wheeler goes roaring past you? What do you feel? Yes, it pulls you in because the increased velocity of the air sucks you to it, decreases the pressure. Any of you were at Talladega Sunday when they didn't run? Okay, good. Okay. We were trying to come home past that, and that was not good. But we thought we were ahead of the thing. Oh, the race is going to go till 3 or so. So we're going to make it by in time. Well, they canceled the race, and everybody was leaving right when we came by. But that's beside the point. But you notice how those teams operate? They usually have a driver, not their star driver, in one of the cars that leads for a while. Yes, and the one behind it is using his drag, not using as much fuel, doing and pull, and that happens not just in car racing. You've ever watched the bicycle races, the horse races, just about everything. Usually the one they call the pace, they don't call it pacemaker, that's what you put in the car, but it sets the pace. The pace car, isn't that what it's called? At the very beginning. Whoever is setting the pace for the rest of them, everybody sort of follows in behind. But then sometimes this guy is going to, or gal, or whoever it is going to have to fall behind. Because they've been overcoming, and the others have been using Bernoulli's principle. There was one specific horse that didn't work too well with. Y'all probably don't remember. You may remember his name, but you were not born probably. Secretariat. Anyone ever hear of Secretariat? Yeah. Okay. That horse was amazing. He would take off and fly. None of the horses could keep up with him to drag. Okay, they couldn't do it. When he won the Kentucky Derby, they say, yeah, but this is short. He'll never make it in the, whatever the next one, the Preakness of the Belmont. I don't remember which. Never make it in that one because it's longer. Well, in that one, he took off. And wow, but when it gets to, I'll say, the Belmont, that is way longer. He'll never endure that long. Out of the gate, and nobody, I mean, he led each race by longer and longer distances. It was amazing. Okay. But that's all Bernoulli's principle. That wasn't talked about here, but it's still a fun principle. Okay. Now, theories and models. Principles are things that happen all the time. I mean, laws are. Principles are similar to them. Theories, though, are things that we think we have enough basis to at least suppose. These are broadly based sets of working hypotheses. We think this is how it works, okay? It's based on considerable experimental support, but we are still not absolutely certain. They form the framework for your thought and further experimentation. And you keep working at them, and boy, after a while, if it happens over and over and over again, you cannot find any way that theory may become a law or a principle or something like that. Okay? One notable one, I'm not going to get into any major arguments about it, but I've heard some people make this statement. The theory of evolution is not a theory, it's a law. Wait a minute, it can't be. Because, guess what? How can you reproduce it? Okay? You can't. Okay? It happened once. We think this, or at least they think this is how things came about, but there's no testing it. Okay? Big Bang Theory. Nice theory, but there's no way you can, well, let's start over and see if it works, you know? No, we can't do that. Okay? We don't have the power to do that. So, there's lots of things that are theories and are going to continue being theories because you can't reproduce. You can get as much supporting evidence and things like that, but unless you can go back and go through an experiment and test, it's going to stay a theory. All right, let's go on to models. These are collections of theories or even just ideas intended to represent a physical system. Okay? Now, probably in your mind, when you see the word model, you think of a small scale thing, right? That's what I always thought of first, you know, was that. A model car, a model plane, a model ship, you know, something like that. We used to do those when we were young, when there weren't internet and things like that. That was cool things to do. Intended to represent the whole physical system. Now, there are some pretty incredible models out there, but if you were to go to, say, some of the car manufacturers, when they're doing new designs, they do a lot of stuff on a computer, and the models are all set up on the computer. Now, they may get far enough along and then actually build a prototype, sometimes smaller, sometimes regular size, and then put it, say, in a wind tunnel and measure how this is responding to different things. They do that with planes and ships and things like this as well. Those are so big, they have to scale those down. Collections of things intended to represent a physical system. Now, they're useful for regimes either way too small to test or way too vast. Well, like a plane. If you want to test that in a laboratory, you got to have a scaled down model, okay? So things too vast. Or things like Big Bang Theory, way too vast. So they test what they can. They come up with models. Now, here's the key. It can be physical, like I've been describing, or mathematical, which basically is what's going into those computer models, okay? Based on a sketch or an analogy or something like that. Let me give you Well, we're going to do a physical model, so hang on to that one. Let me give you a mathematical one. Not tell you what they were, but early in the process of development of electromagnetic theory, people have finally realized that electricity and magnetism were not two separate fields of physics. They were basically the same thing in different forms. So they began to talk about electromagnetic theory. But they just had these ideas, but they didn't have anything that tied them together. Until the Scottish physicist named James Clerk Maxwell. Now, if you've ever seen his name, you would probably think it was Clerk Maxwell. I did for decades. I thought it was James Clerk Maxwell. I realized the Scots don't pronounce things right, so they pronounced it Clark. It was C-L-E-R-K, but they still pronounced it Clark. James Clerk Maxwell came up with, now he may have had a varying number of equations, but I think today it's down to 4 equations. And these were his mathematical model of how electric fields and magnetic fields interact to form electromagnetic waves. Way before we had the technology to test it. He came up with the theory, the model, a mathematical model. Sometime it seemed like it was something like 70 years after his death. Finally, we had the technology to test them, and a guy named, I think it was Heinrich Hertz, who the frequency is named after. He was able to test those, came out like a champ. Okay, his model fit to a T. Another little ill-known character. Let's see, what was his name? Albert Einstein. Yeah, that's who it was. Some little guy somewhere. He came up with a new theory of gravitation. It was mathematical. It was convoluted. No one could. Well, number one, no one would argue with him because he was right about so much. But there's no way to test it. Finally, in just the last 10 years, I believe it is, an event happened in space. I don't remember if it had to do with an eclipse or something else like this, that the scientists said this was coming in and say, look, we might be able to test his theory here. They tested it, fit like a glove. Okay? So they can be physical or they can be mathematical. Let me give you one physical one. This is one I was thinking of. Early in chemistry research, and we had a slide earlier that said atom, the principles of the atom. People started noticing things. They started noticing that when carbon and oxygen combined together, it was always seemed to be 1 part carbon, 2 parts oxygen. Not by weight, but they always did. If you had, and hydrogen and nitrogen combined to form ammonia, always in certain ratios of the weights, sometimes with the volumes. Okay, people began to say they came up with the principle, law of definite proportions. They always combine certain ways. Well, no one knew why. They said they do it, but we don't know why. Well, along came a guy, I think we mentioned his name, John Dalton, British, English physicist, chemist, I guess mostly a chemist, and he came up with a theory. And he knew it wasn't true. He came up with a model, okay? He said, let's imagine that carbon has 4 hooks. Oxygen has 2 hooks. So carbon dioxide, 2 hooks of hydrogen, of oxygen, do 2 each on that, there's your 4 hooks. And it worked when you did hydrogen and water. Hydrogen had 1 hook, oxygen had 2 hooks, 1 hydrogen here, 1 hydrogen here, H2O, water. And he started doing this for lots of them. Came up with a pretty good idea. It seemed to work just about all the time. Now, probably even John Dalton would have said, I doubt if they really are hooks. But that was his physical model that he used to describe it. Now we know what they are. Shared electrons, electron pairs. Electrons always like to be in pairs. So one electron from oxygen, and one from hydrogen, one from the other. It's always a shared pair. That's what the hooks were. They weren't really hooks, but that was his physical model of what was happening before we had any way of knowing there were even electrons involved. There were electrons. We didn't even know about electrons. So here's another physical model, somewhat mathematical as well, the model of a rainbow. Now, I don't know if you can see it from where you're sitting, but if you have your text, I don't know, yeah, several of you have picked up text. The one in your book is turned the other way from this one. Is probably a prettier picture. But here is the first rainbow, and there's the second one. You can just barely see it from here, so you may not be able to see it from where you are. If you look at your book, you can see the first one always. Now, remember, let's back up a minute. Collections of theories or ideas intended to represent a physical system. Okay? You start with observations. Here's the first observation. Which rainbow is the brightest? Inner or outer? Okay, is that always the case? Always the case. Okay? Now, yours in your book, you can probably see it better than this one here, but you can barely see it here. Here, the light colors here are, it's hard to see a violet because it's almost the blue of the sky. Violet, blue, violet, indigo, blue, green, yellow, orange, red, from inside out. But look at the outer rainbow. Red, it's hard to pick out the colors, but the red's on the inside, the greens and blues on the outside. So they reverse the colors. Just sometimes, every time. Another observation. Well, this one you can't see from here, but I'll ask you to. Next time you see a rainbow, or the last time you saw a rainbow, do you remember what time of day it was? Morning? Okay. Anyone else?
It was about 1 o'clock.
Really? You saw one around 1? Wow. Okay.
I've seen one in the afternoon.
Say again?
I've seen one in the afternoon.
Okay, afternoons. I think you'll find out you see most of them mornings or afternoons. Generally later in the afternoon. And when you see one, the next one you see, look for the sun. You know where it's going to be? Behind you. If the rainbow is there, the sun's always behind you. Always. Okay? Always. Okay? Observations. Now, here's what the model is. These result from the reflection and refraction. Now, reflection is when light goes in and bounces off. That's a reflection. Refraction is when light goes in and bends, but doesn't bounce. Okay? Reflection and refraction of sunlight within the individual raindrops. So here's one of your assumptions. You got to make some assumptions. All the little rain droplets are little spheres, right? At least as close to spheres as they can be. That's just nature. Nature always tries to minimize the surface area, so that's going to form a sphere. So these are the little spheres, and here's what those little spheres do. Okay? Here's sunlight coming in. Sunlight's always coming in fairly close to parallel. Okay? Because the sun's so far away, the sun rays are coming in parallel. Now, when they go between the air and the water, that is an interface. Water has a greater index of refraction than air does. So, it starts splitting that light. Have you ever fiddled around with a prism? No. Okay. Yeah, okay. But even an oil spill, anything will do this. it breaks light into different colors. Okay, that's what makes a rainbow. Okay, well, because the red is a longer wavelength, lower energy, violet is shorter wavelength, higher energy. At least according to this picture, the violet gets bent more than the red does. Okay, and all in between are in between there. So that's your refraction, the bending here and spreading of the white light spectrum. But then, when it hits the back of the raindrop, it has what they call total internal reflection. That only happens at certain angles, and that angle happens to be, well, not quite 42, but it turns out being 42. That's when that does. When you hit up here, it doesn't. When you hit down here, it doesn't. That angle right there will give you total internal reflection. But when that happens, it reverses the colors. Okay? So, they reverse. They don't at first, but they do here because now it's refracted that way. And so it comes out red on the bottom, just like I'm sorry. This is sort of backwards. I think they've got their colors backwards, but we won't worry with that. It just, you get that. Okay? But then it refracts again when it comes out, but it doesn't go back together. It spreads even more. That's part of refraction. Your observer sees the rainbow like this. Okay? Now, see, if this was hitting the bottom, the bottom part of the raindrop here, then the refraction would be up here, and the colors would be like this here. But when sunlight goes in and just barely catches the edge of that droplet, it splits again and reflects again, but then it hits here at a place where it reflects again, reflects the second time, and then comes back out, but that second reflection flips the colors twice, so they come out opposite to what these do. Okay? Now, let's think about the things we notice. The sun always has to be behind you because the raindrops are reflecting back towards you. Sun has to be behind you and always is, and always will be. Okay? Number two, this is a brighter one because more sunlight goes through this range than goes through that little tip down there. Okay? So that's why the interval's always brighter. And the angles are always the same. 42 degrees here, 51 there. Okay? Oh, this is a strange way they drew that one, but it is 51 degrees. So the outer one's always the dimmer one, if you ever see it. Sometimes you don't see the outer one. It's so dim. But the inner one is always brighter. If you see both, it's always brighter, and the colors are reversed. So our model fits our observations really well.
You said one is 42 degrees and 51 degrees?
What's that?
You said one is 42 degrees and the other is...
Yeah, the outer, most of the time what you see there, if you were to take a compass and point right to the center of that rainbow, right where the center seems to be, and then span out to the rainbow from that center, you'll find it very close to 42 degrees. If you do see the second rainbow, it goes to 51 degrees. Okay? Because of the geometry here. It has to be. Anything in between this isn't going to produce. Right up here will produce it. Right down here will produce it. Right here will produce it. But the stuff in between, that pretty much goes straight through with no reflection. You have to have that total internal reflection. One for that one, two for this one. And that's why the colors get reversed. Okay. That's one physical model. There's some math in it too. Okay. Another one, and I don't think they show it here on the slide, but they show it in your book. Cartographers or somebody noticed many years ago that, wow, South America looks like it can almost fit into the armpit of Africa, doesn't it? And look how the North America slopes that way, but Europe slopes the same way, the land is sloping out here and here. And this in part of Africa could almost fit in the Gulf of Mexico, Caribbean area. Okay? Someone observed that and said, I think our continents are drifting. The rest of the scientists of his age said, are you nuts? Continents don't move, they're fixed. How can a continent move? It's not floating around there. It's fixed in space. It cannot move. They laughed him out of the society. He was no longer considered a valid scientist. Now I'm making up parts of this. I think it's okay though. That guy's nuts. You can't believe a word he says. But what do we know now? Yes, plate tectonics. The Earth is made out of plates, big plates that do float on what they call the asthenosphere, but they do it awfully slowly, because they bump into each other, they do all sorts of stuff. But we do know plates do move. So we do think that there was once one big continent called Pangaea, and the others. And by the way, the reason that Africa was at one time separating from Europe, or Europe separating from Africa, one, and this part of Asia is separating here. The Dead Sea is happening because the plates are spreading there, okay, and getting further apart. And that indeed Australia used to fit up in the Indian Ocean, they think, It seems to work. Okay? Those are all theories. You can't go back and put the pieces together again and say, will it do it again? Can't do it. So they're theories. That finishes Chapter 1. For those of you who have been in my Physical Science 1 class, whatever year you may have done that, you'll know I say this just about I'll say it every chapter. Nothing replaces reading the chapters. You got your books now, or at least most of you do. Nothing replaces reading the chapters. There's no way this slideshow is going to cover everything. There's no way I'll think of covering everything. And you don't have time, you don't want to sit and listen to me try to think of everything, okay? Read the chapters. But at the end of every chapter, you have a summary. Now, this summary is about moderate length. You have a lot of italicized words in there. Those are usually pretty important. And you'll see them show up again under the key terms, or at least most of them. Those are pretty important. Now, the key terms are listed alphabetically, but they do give page numbers where they're either first defined or first described, so you can check them out there. There's only one major equation here, summary of equation, but remember for every equation that you have, like rho, density is equal to mass per unit volume, you can come up with two different equations that solve for the other two quantities. Volume is equal to mass per unit density, and mass is equal to density times volume. So even though there's only one equation listed, there are actually three equations buried in there. All right. Now before we turn the page, just about every chapter has a person behind the science. They call it people behind the science. The one who's featured in Chapter 1 is a woman named Florence Bascom, a U.S. geologist, an expert in the study of rocks and minerals, founded the geology department in Bryn Mawr, I guess is how you say it, college in Pennsylvania. It has quite an interesting background for her. Guess what? You can write on Florence Bascom if you choose. This can't be your source. I've read this. I'll recognize if this is what you do. You have to go outside the book to get your source. But she's a great topic, so you could do it. Now, but when you read through this, you'll also find out several other names are mentioned. For instance, I just happened to see George Huntington Williams, Mary Holmes. I see the name Johns Hopkins, who was a person, but it's also a university and a hospital. So anyway, you'll see more than just one person mentioned here, and you can find several potential paper topics right there.
So this is for the research paper?
For the research paper.
What are the guidelines on the research paper? Like,
Okay. Yeah.
you can just choose anybody or
Say again?
what are the guidelines for it? Like, you can just choose anybody or, I mean,
Okay.
I missed when you said it. You said
Yeah.
choose
Yeah. Any person, any theory, any phenomenon, any application, if you'll go back and listen to the first class.
I couldn't. I tried to pull it up yesterday.
Okay, yeah, okay. I don't have the link out there yet, but when I do get it, and hopefully it'll be maybe even this weekend, then you'll be able to pull that up.
When is it due?
End of the term. But please get it done earlier than that. Remember, if you get it done this month, the month of October, 2 bonus points. November, 1 bonus point. December, you get your score. No bonus points. Okay. Now, also on page 21, or starting on page 21, but going through page 23, there are applying the concepts. These are multiple choice questions, okay? 44 of them, which is a bit shorter than most. Usually they're closer to 50, but this is pretty close. And if you know those, and the answers are all given here, but don't look at the answers first. See if you can figure out the answers from your reading and that other stuff, and do it. Then look at the answers. If you miss any, see if you can figure out why you missed it. If you can't figure out why you missed it, come to class with it and say, hey, I can't get this one. Why is this the answer here? Either they made a mistake here, or there's some answer and we'll work through it. Okay? So, those are great things to study. Then there are questions for thought. There happen to only be 10 of them for this chapter. That's way fewer than most chapters have. Then there's further analysis. There's 7 of them. That's more than most chapters. Usually they're around 4 or 5. And then there are the Group A and Group B parallel exercises. These are a lot like the examples that we worked in class. So if you can do these, especially the Group A's. Now, y'all with the little books, can you find the answers to Group A's anywhere in the back? Did you look for them? The last copy I saw, I couldn't find it. I specifically asked the lady when she did the custom text, I said, please include the parallel exercise answers in the back. I couldn't find them. So it doesn't matter. It used to be Group A were in the back and Group B weren't. I guess they didn't put them in there. Sorry about that. But still work on them. If you have any questions about them, bring them to class and we'll answer those questions. So that's good things to study for your test. Now, the test on this chapter is going to be different from most tests. It's going to be a lot of fill in the blank. I can think of at least several problems to work that you're going to have to work. So it'll be a little more mathematical. There's at least 2 or 4 problems to solve. There's a couple of multiple choice, and there's several that just fill in the blank. So now here's another thing. Those who've been in my class before know this. Those who haven't, let me say it now. Everybody's here. You can bring with you to every test, including the final exam, a formula and equation sheet. Anything you want to write on a single piece of paper, front and back, as small as you want to write it, as big as you want to write, I don't care. You can bring one piece of paper and have it. This is not a memorization course. I don't like memorization. I don't memorize well, but it's get the information, know how to use it. Okay? So you can bring with you a formula and equation sheet for every test, including this first one. All right, any questions? The last 30 minutes on Tuesday will be the test on Chapter 1. It'll be a bit more quantitative than most tests will be. It's only going to be one piece of paper. I think there's 10 questions, but there's multiple answers, so it's going to be more than 10 answers. So just be ready for that. The questions they asked in the test bank were just pathetic and nitpicky, so I reformulated them so you could come up with everything you need. Okay. Any other questions on that? I'll try to have the PowerPoints and other things out by Tuesday. I can't swear I will, but I'm going to do my best. Okay. Now, let's move on to chapter 2. Chapter 2 is a long chapter. Chapter 1 was pretty short. Okay? It's going to come up in a few minutes, I think. PowerPoint is usually pretty slow, but I don't see it doing much but flashing. So let me try it again. There we go. And it's still slow. All right. Let's go from current slide. Now, in several of the texts that I've taught with from before, either physics or physical science, usually they break this into 2 chapters. They will describe motion in one chapter and explain motion in another chapter. This book puts them all into one. That's why we're going to have 3 different labs for this one chapter, and it will take us a while to get through it. But this chapter is motion. The core concept, if you got your text, you'll see this is, assume your pages are about the same as mine, page 25. Core concept. A net force is required for any change in a state of motion. So that's, assuming you know what motion is, that's explaining why motion happens. A net force is required for any change in the state of motion. It's a good core concept. We got a lot of work to do to build up to that concept. So here's how we're going to do it. And like I said before, this is sometimes done in 2 chapters. This book does it in 1. First we'll describe motion, and then we'll explain motion. Other courses, the books I've taught from, that would be 1 chapter, that would be another. Now, this one does throw in applications all along the way. So that's pretty good too. Okay? So, the title, the first question here, what in the world is motion? First we'll describe it, then about halfway through the chapter we'll start explaining it. Okay, so here is describing motion. First part of the chapter. 3 basic concepts. First is the concept of position. Motion occurs, you were here, you wind up there. You had to move, right? If you were here and stayed here, you're not moving, right? But if you were here, wound up somewhere else, you have change of position, of course. Now, that change of position, if you were a giant sloth, it may take you a long time to get from here to there, okay? In other words, your speed would be quite slow. If you were faster than a speeding bullet, you would get there very quickly. So the second basic concept is that of speed and velocity. Now, what is the connection between position and speed or velocity? There's one new feature in there. Time, okay? A change of position takes a certain finite time to happen. If the time's really long, that's a very low speed. If the time's very quick, that's a very rapid speed. Okay? And then the third one is what? How do you define acceleration? Let me go back and define this one for you. We're going to do it later too. This is a change of position divided by a change of speed. A change of time. Now that is what we often call the time rate of change. That means you're dividing by time. And that's something that physicists love to do. You'll get one concept and say, well, what happens if we change the time on this? Okay? That gives you a new concept. So the time rate of change of position is speed. Guess what acceleration is? Speed divided by time? Yes, you got it. The time rate of change of speed or velocity. How do you describe acceleration?
The amount of force.
Okay, now you're talking about forces when you're involved with it, but if you're bragging on your car, you say I can go 0 to 60 in,
I always say
so, yeah, something like that. What are you talking about? 0 to 60 is a change of velocity, right? From 0 miles per hour to 60 miles per hour. That's what you're talking about, right? In so many seconds. Change of speed per time, that's acceleration. Okay? So, applications of this, after we define those things, then we'll do horizontal motion on land or anywhere, falling objects, that's vertical motion, and then we'll do compound motion, that is both horizontal and vertical change. The first lab we'll be doing, it won't be horizontal, but it'll be single dimension, one-dimensional motion. Then the next lab we do will be compound motion. We really don't do any just falling objects. They just happen so quickly, it's hard to make measurements on them. So we'll do the measurements with compound motion. And then we'll get to some of the others. Okay? So this is the first part of the book describing motion. So let's start with, okay, then the second part of the chapter, I said book, the chapter, will be explaining motion. That's where Jay's idea of forces came in. Okay? They certainly are involved. That was in the core concept, remember, and net force is required. We'll also talk about the basic ideas of inertia and mass. Okay? And we'll talk about Newton's law. These all explain motion. Then applications of these will include momentum and impulse. That will be part of the third lab. Circular motion, we'll just describe that. And Newton's law of gravitation will describe that. And that, in fact, impacts satellites. So the third lab will be forces and momentum. Okay? They're very short labs, so I combine them into one lab. Okay. So that's the second, approximately half of the chapter will be explaining motion. That will be the last lab. The first two labs for this chapter will be describing motion. One-dimensional motion, then two-dimensional motion. So let's start with measuring, which is partly describing motion. Okay, two fundamental components. Anyone remember what one of them was? Position, okay? Now that is also, I think someone said distance. Very good way to describe a change of position. A distance, change of distance. So that's your change in perception, in position, okay? And then the other component is the change in time. That's the second one. Two fundamental components. Remember back in chapter 1, we talked about some of the quantities we measure. One of those was position, distance, measured in meters, centimeters, millimeters, kilometers, miles, feet, inches, furlongs, whatever, fathoms. Time, usually seconds, or hours, decades, okay, whatever. Now, here's a car batting along. By the way, describing motion was 2.1. We didn't do a great job of that, but we talked about position, velocity, and acceleration without defining them, but we talked about it. We're in 2.2 now, which is measuring motion. And this is an illustration similar to your figure 2.2 in your book, but not quite the same, pretty close to that. So here, if you happen to be standing off at a distance and you mark the car right here when it passed as time 0, or position 0, and it went 1 mile and it took 1 minute to do so. You have a stopwatch. And it went the second mile, you have mile markers down there, and you pass the second one 1 minute after that. And then he passed the third mile marker 1 minute after that. Then the 4th mile marker, 1 minute after that. Okay? What was the change of position between here and there?
4 miles.
4 miles. How long did it take?
4 minutes.
4 minutes. Okay? Now, what would you estimate his speed to be? Exactly, because he did a mile a minute. That was his rate of change. 4 divided by 4, 4 miles per minute. Notice your units are your friends. Miles in the numerator, minutes in the denominator, 4 miles per minute. But that's 4 miles in 4 minutes. That's 1 mile per minute. But if you think about an hour has how many minutes? 60 minutes. So that's 60 miles in 60 minutes. Just like it's 4 miles in 4 minutes. So that's 60 miles per hour. Better be on the expressway. Well, major highway for that. Not in town. Okay. Now, let me give you something that the book really doesn't do much, but I do a lot. When I'm talking about change, I use a symbol. Can't use that one. Okay. For change, I use a symbol delta. Delta is a Greek symbol. That's a capital delta, by the way. And the reason they use it is difference. Delta difference. So a delta P, sometimes delta D for distance, delta X if it's on the x-axis, delta Y if it's vertical. You could use anything delta. What that means is the delta means, for instance, this one, Y final minus Y initial. Difference is subtraction. So this is Y final minus Y. So guess what change of time would be? Delta T. And that's always T final minus T initial. Okay? We don't go back in time no matter what the movie said. We always go forward in time. It's always T final minus T initial. So I'm going to use a shorthand delta. The book may use it in a couple places, but there are many places they should use it and they don't. Okay? Now, can I keep trucking here? 3 important combinations of length and time. We've already given them to you, I think. What are they? Anyone remember? Speed, velocity, and acceleration. You got it. Okay? Now, the book doesn't go into this very much either, but I'm going to emphasize it a little bit. Okay? Speed and velocity in everyday English, we use those interchangeably, don't you? What's your velocity, what's your speed? We're meaning the same thing, don't we? In physics, there's a slight difference. And I'll give you this. Speed is a change of distance per change of time, where velocity is change of displacement per change of time. And they almost sound the same, don't they? Here's the difference. Distance, the distance from me to one blank on your name. Diamond. From me to Diamond. That's fixed. Well, the distance from Diamond to me is the same distance, isn't it? All right? When I drove from home to work today, if I drive back the same way, the distance is the same. But displacement isn't. If I go from here to there, I'm displaced that way. But if Diamond came from there to here, she's displaced in a different direction. So velocity deals with direction. Speed only deals with distance. The distance part is the same. The direction part. This has no direction associated with it. This does. Does anyone know what a quantity that has both magnitude and direction is called? It starts with V. Second? Vector. A vector. It starts with VE, in fact, okay? Whereas something that has only a magnitude, the physics word for that is a scalar, meaning it only scales up or scales down. It doesn't have a direction. Speed is a scalar, velocity is a vector. SSVV. Pretty easy to remember that way. Okay? Now, acceleration is always change of velocity for change of time. Even though we'll say change of speed for change of time, no, acceleration is change of velocity. Because acceleration is also a vector quantity. You're always in some direction when you're accelerating. And that's going to be important later too. Okay. So, let's start with speed. Change in position with respect to time. Okay? They're going to come up with a formula. I was starting to write it. Let's do it. Now, the most common thing we usually measure with this is average speed. For instance, you're driving down the highway, you're really trying to be specific about it. When you mark past this mile marker here, and then later past another mile marker, however far it is, and you determine the time that it took you from getting this mile marker to that mile marker, that's a change in position with respect to time. You're not worried about what direction you were going. You could be going around the curve or anywhere else. Doesn't matter. Your distance divided by time. That's what speed is. And usually the time is some finite time increment. Okay? They're going to give us the, let's see. There it is. Speed is equal to distance divided by time. Again, distance has no direction associated with it, so neither does speed. Time, of course, is a scalar quantity. Time is always scalar. There's no direction with time. You can't go back in time. It's always forward, so there's no direction in time. And the distance is not either. So here's your formula. Now, the book uses a shorthand for that, and I really don't care for it that much, okay? Because they use an italicized V. Okay, now I can't write italics, so that's my best shot at it. That's not a bold V. A bold V would be a vector. Italicized would be a scalar. Now they also use a bar over it, which is okay. That means average speed. That's what average means. The bar means average. And that would be, how I like to say, is change of distance over change of time. They just say distance over time, which is okay. It's all right. It's not confusing. But it's your distance traveled divided by the time it took you to travel it. That's your average speed. Because you always have a finite time that it took. Okay? Now, they talk about another concept here called instantaneous speed, where the time interval is approaching zero. Well, you see you have a problem with this if that's zero, right? You can't ever divide by zero. Ever divide by zero. So this is getting into a concept that we deal with in calculus, which is a limit as this is approaching zero. We're not getting into that now, but that's what instantaneous speed is. So if you're in your car and you're measuring mile marker to mile marker, looking at your watch, how long does it take? That's your average speed. More likely, it's this. You've looked at your odometer at the beginning of the trip, or when you filled up with gas, and then you measured how far you went the next time, or if you're on a trip, how long it took you to get that far, and sure enough, that's your average speed. Now, just a sort of a dumb story here. After I graduated from college, I went to the Navy. I was on the Navy ROTC scholarship, so I had my obligation. And my first duty station was going to be out of, they probably say Concord, California. Actually, the town was Port Chicago, California. There is no town there. I was on an ammunition ship. And back during World War II, they were filling, it wasn't a naval ship, it was a commercial ship. They were loading it with ammunition and someone dropped something and there was such an explosion. The whole ship full of ammunition blew up, wiped the town slick. There was no Port Chicago left, except they rebuilt the piers. Okay, so there was no Port Chicago. The closest town was Concord, which was miles away. And anyway, so I was driving to the West Coast, but my ship wasn't in port then. My ship was coming back from a Western Pacific deployment. So they decided to fly me to Guam to pick up the ship and then come on back with them. So I was living in Georgia, drove across to San Francisco to catch the flight to catch the ship. And as I was driving out, this was back when many states had speed limits of 75 miles per hour. I don't know if any had any greater than that, but I was wanting to make sure I got there in time, so I was driving at least the speed limit just about the whole way. And I was keeping up with my gas mileage and stuff. And what I figured is I would drive out west, especially back then. You didn't want to get less than half a tank of gas because you never knew how far it was to the next gas station. So that's what my goal was. Use half a tank of gas, stop and get gas. And I had y'all won't remember this, a little old Plymouth Duster, slant six engine, okay? It got pretty decent gas mileage, and I was driving speed limit going out. And I would go about 4 hours between in a half a tank of gas. And I tried to just keep trucking, and 4 hours was pretty good. I'd get up in the morning, eat breakfast, hit the road. 4 hours later, stop, have lunch, rest, then hit the road, go 4 hours, fill up with gas, maybe go another 4 hours, stop, eat supper, get a place to stay, and spend the night. That's what my travel plans were, and pretty much I did that all the way out. I kept up with gas mileage the whole way. I just was weird that way. When I came back, we had the gas shortages and all this kind of stuff. They had dropped the speed limit. Also, I knew that you got better gas mileage if you went even a little slower than the speed limit. And so coming back, I probably averaged between, speed limit was 55 by then, not 75, not 70. And I stayed between 45 and 55 most of the way back. Number one, it took me longer to go the same distance because I was driving a slower speed. Number two, I was getting much better gas mileage, so it took me way longer to use half a tank of gas. So sometimes I just had to stop and eat, or get out and rest or something. Average speed. Mileage over time, okay? That's how you do average speed. Now, your odometer and your watch will give you average speed. What gives you the closest you got to instantaneous speed? Your speedometer is telling you almost instantaneously what you're doing. Now, notice I did my hand like this. The old days when I was driving across, that was an arrow that went like this, okay? Nowadays, there are numbers that pop up there, right? Any of you still have an arrow? Oh, look at that. Good for you, okay? Most cars now just have digital, okay, readouts there for, that's your instantaneous speed. As the time interval is approaching zero, telling you exactly, or as close as they can, what you're driving instantaneously. Okay. This is the picture that's in your text on page figure 2.2. This is the one, very similar to what we had before, except this one is measured, okay? And this one didn't start at 0, it started at 50. So, average speed, how far did you go from this point to that point? 100 kilometers. How time did it take you to do so?
3 hours.
2 hours. So what were you averaging? 50 kilometers per hour. A lot slower than you were in the last one. 60 miles per hour, a mile longer than a kilometer. Wow, you're poking here. Okay. That was 50 kilometers per hour. Okay. Oh, your time difference? Remember, it's a difference in time? It wasn't 3 hours, it was 3 minus 1. Delta, final minus initial, final minus initial. That's why I put the delta in there. They just say, well, you have to do this. And they did it. Elapsed time was 3 minus 1. Elapsed distance, they didn't say it, but it was, maybe they're going to say it next, is what is your average speed? This is speed because it's not a bold V. And that is 50 kilometers per hour. Are they going to do it? I guess not. Okay. But you did it in your head. Good for you. Okay. Oh, and by the way, when you have an equation like this, guess how many other equations you can come up with?
2.
2 more. Okay. And what are they?
V times V.
Say that again. T times V is equal to D. There's one.
And D over V.
D over V is equal to T. Absolutely. You got it. You can use those triangles or circles if you want to. Those are your 3 equations you can get out of this one. 2 that you can get out of this one. Okay. Now, what's the difference? We've already said it. In velocity and speed?
Velocity is the
Direction. The direction. Okay? This describes, velocity describes your speed by its magnitude, how fast is it going, but also with the direction. Which direction is it going? So when I drove from home to here this morning, let's say that I averaged, let's say 70 miles per hour. It'd be a lot easier to, I'd say I average 60 miles per hour, because it's real easy to do that way, right? So 60 miles per hour, because I was sometime in town and front end and back end on the expressway closer to 70. Okay? Except there were some trucks, so that slowed down some. But the velocity tells you how fast, well, the magnitude of your velocity is your speed most of the time, okay? But the velocity also has the direction. So when I drove here this morning, let's say I averaged 60 miles per hour to the southwest, because I live in south side of Birmingham. Bessemer is a little bit to the southwest. And when I drive home this evening, it'll be same 60 miles per hour probably, same distance anyway. It may take me a little less time because there won't be as many trucks maybe, but it will be to the northeast, okay? Because the directions are different, the velocities are not the same. Even if the speeds were the same, velocities are not, because velocity includes direction, okay? Graphical representation of vectors, they do mention them here. The length is your magnitude, and if that's a velocity vector, that length will be your speed. The arrowhead indicates which direction you're going. Okay? Now they do this, but they don't do a lot with it. Okay? So here's a car, or some sort of vehicle, traveling 30 kilometers per hour to the east. There's your speed, your magnitude, with the direction, that's your velocity. So they represent that with an arrow pointing to the east with a certain length. This one, however, is going 60 kilometers per hour to the northwest. So you would take the same magnitude, but double it. That gives you your 60 kilometers per hour, but the direction is to the northwest. Or you could take the same direction to the east and just double the velocity, and that gives you 60 kilometers per hour to the east. Velocities and speed always have to have distance per time. That's your formula, that's your units. Kilometers per hour, miles per hour, feet per second, centimeters per second, whatever it is, furlongs per fortnight, whatever it is, okay? You have to have distance over time. Okay, does that make sense?
So for the test, we have to have conversion for those, like kilometers to
Okay.
inches and all of that?
I don't want you memorizing any kind of stuff like that. If you need something on the test and I don't give it on the test, ask me and I'll give it to you then. Okay. That's not what the testing is over. It's the concepts is what I'm testing you over. So I'm going to try not to have all those silly I'm sorry, those little things like that. Now, by the way, these are going at the same what?
Direction.
No, not the same direction.
Speeds.
But their speeds are the same, but their velocities are very, very different because they're in different directions. Okay. Now, remember this phrase, time rate of change of, okay? Well, speed is time rate of change of distance or position. Velocity is time rate of change of displacement, which is a vector quantity. Acceleration is the time rate of change of velocity. Now here they say motion. So you can almost, in this chapter and most of the subsequent chapters, when they say motion, think velocity. The rate at which your motion is changing. Your velocity is changing over time. Okay? The rate at which the motion or velocity is changing over time. Time rate of change of velocity. Now, to have an acceleration, you can have it in several different ways. Your speed can change. That's always an acceleration. Even when it's slowing down, that's a negative acceleration. You're accelerating in the opposite direction. Because your change of velocity was fast here, slow there, your time was increasing, okay, so it's a negative. The velocity changed over time. Okay? So the speed can change, but also direction can change. Because remember, acceleration is time rate of change of velocity. And if your velocity is changing direction, that's a change of velocity. Right? Because velocity matters, direction matters. Even if you're going the same speed. So if you're going the same speed around the curve, you're accelerating. You are? Sure you are. Think about if you're doing it too fast. What are the tires doing to the road? Screaming, sliding off, exactly. The road is trying to, and your tires are trying to push you to the center. Okay? You are accelerating if you're going around. So your direction could change. Or you could be changing both your speed and direction, and that's another kind of acceleration. And acceleration can be negative. If your initial velocity is faster than your final velocity, then the change of velocity is negative. Time is always positive. The change of time is always positive. So, here's some examples. If you start off at 30 miles per hour and wind up at 60 miles per hour, what's your acceleration? Oh, they don't give you a time here. Okay, forget that. So, this is a change of velocity in the same direction. Your speed is changing. Here you can start off at 60 miles per hour and wind up at 30 miles per hour. What are you doing? Change of velocity. That's a negative acceleration because 30 minus 60 is negative 30 in whatever time interval that's in. This is a positive acceleration. That's a negative acceleration. The speed is decreasing. Here, you started off going west and wound up going east. Did you accelerate? Because your velocity was changing. 30 miles per hour, your speed didn't change, but your velocity did. Because you were going in that direction here, this direction there. Definitely had a big change of velocity, even though your speed was constant. Or, if you started off 30 miles per hour in this direction, wound up 60 miles per hour in that direction, you really have a big change of velocity. Because this is a positive 60 minus a minus 30, it's a positive 90. Minus a minus is plus. This is starts off a negative 30, winds up to positive 30. That's a change of 60. So it's definitely a change of velocity. Make sense? Even if your speed is not changing, if your direction changing, you're accelerating. All right. Now we talk about a concept we're going to be using a lot. We won't always say something about it, but we're going to use it a lot. It's called uniform acceleration. That's constant straight line acceleration. What we mean by that, would that mean your speed's the same? It could be if that constant acceleration was 0. Because remember, acceleration is a change of speed. So if your speed's the same, you have 0 acceleration, right? Oh, wait. If your velocity is the same, you have 0 acceleration. And if you're a straight line, then your direction's the same. So the only way that speed could be the same would be if you had 0 acceleration, which is constant, okay? But if it's acceleration of 1 meter per second, then you're increasing your speed because you have a positive acceleration. -3, you'd be negative acceleration. Even though you may still be moving in this direction, your acceleration can be that way, slowing down. Okay? Now, when you have uniform acceleration, meaning your acceleration is constant in the same direction, then your average velocity is simply related to the initial and final velocities. Okay? If it's a uniform acceleration, constant straight line acceleration, then your average velocity is, you have final minus initial, it's always the same number. If they're the same, that number is 0. If this one's larger than that one, then it's a positive. If this one's smaller than that one, then it's a negative. So that would be uniform acceleration if that acceleration didn't change. Most of the time your velocity will be changing, unless it's a 0 acceleration. All right. And here is a formula we'll be using not in Tuesday's lab, but in Thursday's lab. This is with uniform acceleration, constant straight line acceleration, then your average velocity is your final plus initial divided by 2. Just like your average score. If we had taken 2 tests, what would be your average score? Add 1 to the other, divide by 2. Okay? That's your average velocity only when you have uniform acceleration, which means constant acceleration. Your average velocity will be the sum of those two. Now we actually have 2 formulas then for average velocity. Remember the first one? The first one was change of position over change of time. And in the second lab we do, the one that we'll do next Thursday, we'll first calculate our average velocities this way, and then we'll calculate it that way. That's how we come up with the final velocity. Okay. Whoa. You know, I've gotten to paying too much attention to my slides and not enough to the examples. So I'm sorry I did this last time. I wasn't going to do it again, but here I've done it. Okay? All right. Okay. Example 2.1 on page 28. The driver of a car moving at 72 kilometers per hour. 72.0 kilometers per hour. Now, what's that a measure of? You're going to find me asking this question just for every time I write down a quantity. What is that measuring? That right now is measuring speed. So we'll call that V bar. That's what they like to call it. Okay? Drops a road map on the floor. The driver drops the road map on the floor, and it takes him 3 seconds, 3.00 seconds, to bend down, find it, and pick it up, and sit back up again. What's that a measure of? That's time. Okay? The question is, how far did he travel during that time? Second? Okay, wait just a second. What are we looking for? How far did he travel? That's a distance. That's the unknown here. Now, how do we get distance out of velocity and time? We've got a problem, Houston, don't we? Okay? Here's what our problem is. This time is in seconds. This time is in hours. That's why units are your friend. Write them down. Pay attention to them. You can't do anything to this problem until you get your units to match. Okay? Now, do you think, just for instance, he's going to go as far as 1 kilometer in that 3 seconds? I don't think so. So let's get that speed unit down to something more reasonable. Like, let's convert the hours to seconds, but also convert the kilometers to something shorter. Meters. Very good. Okay? So let's do that. Now, this is a legitimate thing you could be doing on a test. I'm not saying I will have you doing it, but this would be legitimate. What we've got to do is unit conversions. Now, there's lots of ways to do it. If you have a good way to do it, more power to you. Here's how I suggest doing it, because it seems like this works for me, and it seems to work for most students. I'm going to put down a series of double blanks. Okay, that may be enough. And we're trying to get to meters per second. So we'll have seconds where we want it, meters rather than that. So you see there's 2 conversions we got to make. One of these, we've got to get our kilometers to meters, and we've got to get our hours to seconds. Okay? I put down 3 sets of pairs of lines because I didn't know if you could do one in one step or you take 2 steps. So we'll go with that. Which one do you want to do first? Kilometers to meters or hours to seconds? I don't care much.
Well, hours to seconds is obvious.
Hours to seconds is what?
Obvious. That would be easier.
Okay, that you count that easy, okay? How do you do hours a second? You do it in 1 step or 2? Second?
You could do it in 1, you could multiply every how many hours you got times 60 and give you.
Okay. Now, I think I heard something there. Here's my suggestion, folks. Put the units into place. Don't start with the numbers, start with the units. If you're trying to get, like I heard, from hours to seconds, are you going to go through, you sounded like you were going through minutes, were you? When you said 60?
I was going to go 60, you got hours, 1 hour, 60 minutes. So then I was going to times that by 60 minutes.
Okay. Well, let's take 2 steps to do it. Let's first take our hours to minutes. Okay. To do so, we got to put one of those units on top and one on the bottom. Which goes on top? Always put the units in their place. Which goes on top, which goes on bottom? Hours or minutes? You tell me. Where? Hours on top, minutes on the bottom. Now match the numbers with the units. And you were doing that, and what did you say? What's that conversion? 60 what? 60 minutes is 1 hour. Got it. Okay? That got rid of your hours, now you're to minutes. But you still want seconds. So we got another conversion to do. And what's that one? What unit goes where? Always put the units in the place. Second, minutes on top, seconds on the bottom. Cancel out the minutes, you got seconds. How many minutes in a second or seconds in a minute? 60 seconds, match the numbers with the units. 1 minute. Okay, now we've got from kilometers per hour, we got kilometers per second. But we want meters per second. So which unit goes where? Kilometers on top. If you put them on top and meters on the bottom, you wind up with kilometers squared per meter. I don't know what that is. See, kilometers is on top here, so you need to get rid of it. You need to put kilometers on the bottom. Don't you see? Now they'll cancel out. I don't like to talk about canceling out numbers, but you do cancel out units. Do you see why that's true? Okay, now, how many meters in a kilometer, or how many kilometers in a meter? Now match the units. What does kilo stand for? 1,000. So this is 1,000 meters is 1 kilometer, 1,000 meters, okay? That's it. Okay. Now, we've got to do the math. And it's not that bad, but calculators would help. But I'll show you a couple shortcuts. You can divide out a 0 there with a 0 there, a 0 here with a 0 there. That just makes the number smaller. And what you wind up with 72 times 10, that's 720, divided by 36. So 720 divided by 36. I think I can do that. Isn't that 20 meters per second? I don't need it down there. 20 meters per second. Okay? So, 20.0 meters per second, because we need to keep up with our significant digits. 3 significant digits here, 3 there, we need 3 there. You see these conversions, 60 minutes in an hour, that's exact. Okay, you can put as many zeros after that as you want to. 60.00000. That's as many digits as you want. Same with 60 seconds in a minute, as many .00s as you want to. And 1,000.00, you can put as many decimals as you wanted to, but it's exactly 1,000 meters in 1 kilometer. So we want the answer in 3 significant digits, 20.2. Now I like that one better. Now let's worry about the formula. What is the formula to get from velocity, time, and distance? Anyone remember it? Okay, wait. Delta D, is that what you said? Okay, velocity, average velocity is change of displacement over change of time. Okay, exactly. And your change of displacement? Well, that's what we're looking for, the D. So you want to rearrange this to make it work, or you want to plug in numbers first and then rearrange? I don't care. I call it chug and plug or plug and chug. I don't care much. Huh? Which? Rearrange it first. So how would you rearrange that? Yeah, multiply by your delta T, and I can't get my pen to work, my eraser to work. Okay, there we got it. Okay, multiply by delta T here and a delta T there. Okay, here they go out, and you have distance. I'll go back to distance is equal to velocity, average velocity or speed times time. Now plug it in. Average velocity was 20.0 meters per second times 3.00 seconds. That was your time. And what does that give you? Second, 60.0 meters. How far is 60 meters, by the way? Yeah, about 70 yards, right? Yeah, pretty close to 3/4 of a football field. That's how far he went when he was doing this. How many deer could he have hit in that time? You know, who knows what could have happened, darted out in front of him in 60. What's that?
I said, I was being funny. I said, probably 1 deer is probably that's what it's going to take to knock him off.
Knock it off the road. You're absolutely right. Or kids, or dogs, or squirrels, or whatever. Anything could have happened in those 60. That's close to 3/4 of a football field. That he has traveled, not seeing or doing anything at that speed. Kind of scary. And sure enough, that's what they got. 60 meters, 60.0 meters. Example 2.2, can I erase this one? Yay or nay? Okay. All right. Example 2.2, a bicycle has an average speed of 8 kilometers per hour. So that's your average speed, V bar, equal 8.00 kilometers per hour. Now they're doing the same kind of thing to us, aren't they? Okay, now, the thing is, this is sort of crazy. How many bicycles would average exactly 8.00 kilometers per hour? This is sort of a made-up problem. Okay, how far would it travel? So again, we're looking for distance, so it's really the same type problem in 10 seconds. So that's your time is equal to 10.0 seconds. Well, you got the same problem as before. We got to go from kilometers per hour to meters per second. I can't write. Okay? And you got the same conversions. But remind me, what goes where? Always put the units in their place. How would you do it? Same way we did it before. Hours to minutes. Okay. That means hours will go out. How many hours in a minute or minutes in an hour?
60 minutes.
60 minutes, 1 hour. Got it. So that got us to kilometers per minute. But we want meters per second. So what do you do next? Okay, and what goes where then? Minutes on top, seconds on the bottom. That way you can cancel out the minutes. How many minutes in a second or seconds in a minute? 60 seconds is 1 minute. So now we got kilometers per second. We want meters per second. So what unit goes where?
Kilometers over meters.
Kilometers what?
Over meters.
Under meters, is that what you said?
Over meters.
Okay, you did that again, didn't you? Kilometers over meter. That put the meters in the bottom. You want it on top. You already have kilometers on top. That won't work, will it? They won't cancel out. So we need to put meters on top, kilometers on the bottom. And how many meters in a kilometer or kilometers in a meter? 1,000 meters in 1 kilometer. And your conversions do the same. Get rid of a 0 there, a 0 there, a 0, 0, 0, blah, blah, blah. And that gives you 8 times 10 is 80 kilometers. Okay, oh, you cancel out your kilometers. Sorry about that. 80 meters over 36 seconds. Because that's all you got in the denominator. And what does that give you? I'll use a calculator on this one. I'm not going to try to figure that out in my head. A little over 2. Second? 2.22. And that's meters per second. Units are your friends. 2.22 meters per second. That sounds about right. Bicycles don't go all that fast, especially when you're going hours, okay, on it. We didn't tell you how far, but okay. Those make sense? All right. That was examples 2.1 and 2.2 over on page 30. Now we're talking about acceleration, so let's go a few slides. Here we go. Okay, let's put it here. 2.3. A bicycle moves from rest. Ooh, what does that mean?
Not moving.
Okay, and how can you express that in a physical quantity? What is 0?
Your initial.
Which initial? Initial what?
Movement. Your initial start.
Okay,
What did you use?
I would call that your initial speed. If you're at rest, you're at 0 miles per hour, right? So at rest, this is a good one to get. That translates to and it says from, so that's your VI is equal to 0, and they're using units of meters per second. Meters per second. Okay? 2, so that means it goes from rest to this, so that's V final is equal to 5 meters per second. Notice they don't put any significant digits there. We only got 1. N, and here's your time, is 5 seconds. Okay? What is the acceleration? Now, the slideshow, and I'm sorry about this, the slideshow did not give these equations. Let me give you these equations. They gave you the average speed. I forgot they didn't give you the, okay. Here, I'm going to give them to you now. Equation 2.2 on page 30 is acceleration. I'm going to do it a little bit differently. Delta V over delta T. Delta means final minus initial. That's V final minus V initial over, and if you needed it, T final minus T initial. Like if you started at your clock when it was 12:03.77 or something, that's what you would use. Most of the time they give you the time interval, so that just goes into the denominator, which is what it will be in this case. Okay? So, say again?
So this is acceleration.
That's acceleration. Just like, remember, speed, average speed was change of distance over change of time, which is distance final minus distance initial over time final minus time initial. The formulas are almost exactly the same. It's just what you put there. So, now we can do acceleration. What is your acceleration? V final was 5 meters per second. Now this seems stupid, but I'm going to do it. Minus 0 meters per second all over 5 seconds. And what does that give you? 5 minus 0 is 5 meters per second over 5 seconds. What would that be? 1, and it's meter per second, and you could write it this way if you wanted to, meters per second, like Jay's car, he was saying miles per hour per second. That's what you were measuring your acceleration by, but this is meters per second. So the shorthand for that, and it's a little easier to write, is 1 meter per second squared. Now, there's no such thing as a square second, but that's just a shorthand, meaning you divided by second twice, so it's meter per second squared. Just a lot easier to write. So that's your solution for 2.3, 1 meter per second squared. Okay? All right, to erase that one. Oh, and by the way, since we're here, you could take this and write 2 other equations, right? Change of velocity is equal to acceleration times the change of time. Now, if that time is just your time interval, you can leave off the delta. This would be V final minus V initial is equal to A times T. If that's just your time, that's how long it took. And you can add a V initial to both sides, and this is V final is equal to V initial plus AT. Now there's another formula to give at the top of page 30 on the second column. Now, think about this. It's helpful for these equations to make sense to you. So your final velocity is whatever you're traveling initially, and then how much your acceleration increased that velocity, right? So this is what you had to begin with, plus what you changed. Acceleration times time is change of velocity. So that gives you your final velocity. So that equation sort of makes sense, doesn't it? Okay. All right. So, let me erase that. Boy, by Thursday afternoon, I'm running out of gas, okay, in a automotive sense, okay, never mind. Actually, I am running out of gas in an automotive sense if I don't get it on the way. No, I did it yesterday. I'm okay. Okay. So let's do example 2.4. An automobile uniformly accelerates from rest to 5 meters per second squared. What was rest? Okay. Now this is a uniform acceleration, so rest would be, in this case, 0 meters per second from rest, okay, that's always your speed, to some V, this is V initial, to some V final that we don't know. It says, what is the final velocity, okay? And it says at 5 meters per second squared. What you reckon that represents? If they don't tell you, look at the units. That's an acceleration. Okay, very good. And it actually tells you before, uniformly accelerates at this. 4, what's the next thing? 6 seconds. What's that? 6 seconds. That's your time interval. You can either call it delta t or just t. Okay? So, what you reckon your formula is going to be here? We could start with the same one we just used, which was acceleration is equal to change of velocity over change of time. So I'm going to call this change of time. Okay? And we're looking for something to do with the velocity. Let's multiply by your time interval. I'm going to put it behind it in a minute, but right now I'll just put it here. Okay, so your change of velocity is equal to acceleration times your time interval. Okay? Well, your change of velocity is V final minus V initial. We're looking for V final, but what was your V initial? 0 is at rest. So this is 0. So this is equal to A times your time interval. So there's your formula right there. What was your acceleration? 5 meters per second squared times your time interval, 6 seconds. Now notice here on your units, this second will wipe out one of those, but not both of them, and that gives you a final velocity of 30 meters per second. Good unit for velocity. Units are your friends. Be kind to them. They'll keep you out of trouble. By the way, folks, if you remember, that 60, wasn't it 60? Oh no, that was kilometers per hour was 20 meters per second. This is 30 meters per second. You're moving. That's about 90 kilometers per hour, which is going pretty fast. But I'll tell you what, the acceleration of 5 meters per second squared, that's a big acceleration. Big acceleration. You're not going to maintain that for very long because you'll soon be approaching the speed of light or speed of sound of something. So yeah, you're not going to keep that up for very long. Okay, that was 2.4. All right, somewhere in here we must have gotten to uniform acceleration, so let's move on to that. Okay. Let me erase whatever that was there for. And this will be 2.5. An automobile moving at 25.0 meters per second. 25.0 meters per second. Now what's that a measure of? Speed. Okay? So that's going to be our V initial because that's the first thing they give us. Comes to a stop, what does that mean? What 0? Final velocity is 0. Hey, we're slowing down here, aren't we? Okay. In 10 seconds, so what's that a measure of? That's your time. I'm going to call it delta t just for fun. Okay. When the comes to a stop in 10 seconds when the driver slams on the brakes. How far did the car travel while stopping? So what are we looking for? Distance. Now wait a minute. Let's see. This is problematic here because we don't really have a formula that relates change of velocity and time to distance. What does change of velocity and time give you? Okay. Okay. Let me back up and ask it a different way. When you slam on brakes, here's what the assumption is. That you've got a uniform, and we haven't even gotten here yet, but a uniform force trying to stop your car. That's the friction between the road and the tires. Okay? Now, if that's a uniform force, that means we have a uniform acceleration. And let me flick one little thing here. What can this give you? Average velocity in a different way. Here we have a V initial, a V final, and we can do an average velocity based on that. So what is your average velocity? V plus V final over 2, and that would be 25.0 meters per second over 2, which is, y'all can do that in your head, can't you? 12.5 meters per second. Now that you know that, you can come up with a distance if you know the time, right? What's the other formula for average velocity? V bar is equal to distance over time. We'll just use time here. But we're looking for distance, so let's solve that for distance. What would that be? Multiply both sides by time, and that gives you distance is equal average velocity times time. Average velocity, 12.5 meters per second, times your time interval, 10.0 seconds. How far did it travel? 125 meters, because your seconds cancel out there. That's exactly the type of distance you want. Low here, okay? If it takes him 10 seconds to stop from 25, remember 25 meters per second is something considerably more than 60 kilometers per hour. So he's going pretty fast. It's going to take him 10 seconds to stop. How far did it go? That's basically from the back of one end zone almost to the back of the next end zone. More than a football field in length. Because 100 yards would be that. This is 125 meters, so it's 25 meters more. That's way more than.
Yeah, that's like football and about a whole length of football and probably 15 yards, end zone 15 yards.
Yeah, that's a pretty good guess. That's quite a ways. So at that kind of speed, slamming on the brakes when the deer runs out ahead, you're definitely going to have some deer meat. Probably plastered all over your car with a lot of dents, because you're not going to be able to, unless the deer was more than a football field ahead of you, you're not going to have any chance of stopping before collision. Okay? If it takes 10 seconds to stop. Maybe something's wrong with the brakes, I don't know, but that's pretty serious business there. And let's see, what did they get? 125 meters, good for them. Let's do example 2.6. So remember, folks, you can use multiple ones of these to get to your answer. Okay? Uh-oh. I erased 2.5. Let me go back and get what we needed. I can't pull it up, but let's do. 2.5 was the initial is 25.0 meters per second. The final, when it came to a stop, was 0 meters per second. The time interval was 10.0 seconds. Okay? That's what our problem was. Oh, I'm sorry. 2.6 is saying, what is the deceleration of the automobile in example 2.5? So what is your acceleration? Oh, don't tell me we've forgotten that already. It's been at least 15 minutes. What's the formula for acceleration? Change of velocity over change of time. What was your change of velocity? Change of velocity? What is delta always? Final minus initial, always. And what would that be? Negative 25.0. See, your final is 0, your initial is 25, so that, let me write it out. Okay, that might be helpful. Okay. The delta means difference. That's V final minus V initial over your time interval. Okay? And your V final here was 0 meters per second minus 25.0 meters per second over 10.0 seconds. So that's going to be a minus 25.0 meters per second divided by a 10.0 seconds. Okay? What do you get? Negative 2.5. 2.50, because we've got 3 significant digits, meters per second squared, or meters per second, whichever you want to call it. All right, good deal. Okay. Now, by my calculations, we've been at it for what? It seems like it, doesn't it? About 2 hours and 15 minutes or so. But we only got another 15 minutes or so before we are going to stop the lab. Want to keep trucking till then?
Yeah.
Huh? Okay, let's keep going. All right, so let's move on to forces. Okay? I'll try to keep up with the book now, but we only got 15 minutes, so I think I can do this. Let's do a little bit of historical background here. Okay? Way back in the old days, remember those ancient Greek philosophers? We don't quite call them scientists. They may have thought of themselves as scientists, but they weren't quite, because they only thought about things. They never tested things. One of the honchos back then was Aristotle. Boy, if Aristotle said it, no one questioned. And Aristotle came up with a few ideas. Okay? Here's one. Heavier objects fall faster than light objects. It sounds pretty good, doesn't it? Think that's true? Yeah, it's been time to say, I'm not going to make anything from that. Actually, one of the first times I taught physics here, where I was teaching them down in 259, and in the back of 259 there's a door that opens to a stairwell. Of course, the door's always locked. But I got somebody to come unlock the door for me. And I sent my class down into this parking lot down here, and I went up to the 3rd floor. There was a window there, and I had 1 kilogram of mass, that's 1,000 grams, and I had one that was either 1 or 5 grams. So which was heavier? The kilogram, way heavier. And I held out the window and dropped it. Guess what? Hit the ground with 6 feet. Aristotle never did that. He just said heavier objects fall faster than lighter objects. No, that was a ratio of about 1,000 to 1 or 200 to 1. I mean, it was a pretty big ratio. But he thought it was true. Seemed like it might make sense, but he also thought objects moving horizontally need a continuous force, applied force, to keep moving. And it sort of seems like it, doesn't it? Because you roll something or push something, it usually comes to a stop. To keep it moving at a constant speed, you have to keep pushing. Okay? Now, that seems even more reasonable. Okay? But he relied on thinking alone. Along came Galileo and Newton. Now, Galileo started questioning this first. Okay? Newton wasn't even born yet. Okay? And what Galileo did was start running a number of experiments. And just like my little experiment, he found kilogram fell at the same rate that the 1 gram or 5 grams, whatever the real light was. Okay? They actually do fall at the same rate. Now, what makes the difference here boy, lucked out today. These are 2 absolutely identical pieces of paper on them. Right? Same print? Well, no, not quite the same print. But they're the same, basically. So would you say they would fall at the same rate or at different rates?
Different.
Why?
One got more ink on it than the other one. Heavier.
What's that?
If one has more ink on it, by logic, it would be heavier.
Okay, that's according to Aristotle. But it sort of depends on how I drop them, doesn't it? Okay, let me do something. Now, if indeed they're about the same now, but maybe this one has more ink.
No,
So-
that's resistance. It's smaller.
Ah ha ha! You just nailed it. They were the same weight. Same weight, but this one fell much faster, and you got it. Aristotle didn't take into account anything like the forces that were opposing the motion. He didn't do that. So Galileo and Newton, now if I had wadded up the other one and did it, they fall the same way. Okay? So you had something else going on there. Even with this one, there is things, resistance, that's keeping it from moving as freely. No force is required for uniform horizontal motion. Theoretically. Okay? And this is based on measurements. Now what Galileo did, rather than just looking at things sliding across the floor or something, he rolled balls down inclined planes. That's what we'll be doing in the second experiment, second lab that we have, the one next Tuesday. And you'll see, it doesn't matter the weight of the ball. They go at the same rate. Okay? And if they go at the same rate this way, they should go at the same rate that way as well. So, and you see, by rolling things, you get the friction out of it. Okay? The friction's actually negligible then. Okay. So, this is beginning of the concept of forces. Aristotle really didn't think in terms of forces. Okay? maybe what he was talking about had to do with it, like heavy, that means more force, okay? But, okay. Here is a definition for you. A force is a push or a pull. Now, I can remember taking physical science in high school, 9th grade, under Coach Cooley Hubert. He was an old, y'all don't even remember this, single wing. Have you ever heard of that? In football, it's a formation.
Yeah.
Single wing football. Way back. It's sort of a precursor to the option. Huh?
Like a inverted version of wing T.
Yeah. And they changed that from single wing to wing T, and they started going from there. But then when they came out with the option and the, then that got back to the concept. But he had played at Alabama in college, and was on one end of the longest touchdown pass in Rose Bowl history. I don't know if he threw it or he received it, but one or the other, he was there. And he was a tough old knot. Of course, none of the other schools were playing single wing football anymore, and everybody knew how to defend it. So, and boy, he ran his players into the ground. They were in great shape, those that made it. Okay. Well, I can remember having him in class, and he talked just like Bear Bryant did. Now, he didn't play under Bear Bryant. He was older than Bear Bryant. But he'd say, "A force is a push or a pull." So when I receive this, I think of Cooley Hubert. And that's exactly one of the best definitions I can come up with. Very simple definition. A force is a push or a pull. Capable of changing an object's state of motion. Now, I can push on this concrete block wall till the cows come home, and I'm not going to change its motion any, am I? Okay. So that's not going to change it. But a push or a pull capable of changing an object's motion, like if I pull on this chair, yeah, I've changed its motion. So that is a force. A push or a pull capable of changing an object's state of motion. Definition of a force. The overall effect is determined by the vector sum of all the forces, and we call that the net force acting on the object. So let's say we have, now this is a cargo ship. Let's just call it a cargo ship. These booms are for transferring cargo, okay? And are we getting close to out of time? Not quite. Okay. What if the ship was there in the water and you had two tugboats that were able to push with 1,000 units each? 1,000 units of force each. They both pushed on this side of the ship, then the net force on that ship is 2,000 units to the east. And they're going to move the ship. But what if they come out there and they don't know each other's there? And this one thinks it needs to be pushed to the east, but that one thinks it needs to be pushed to the west. And now on the opposite side of the ship, they don't see each other. What's the net force on the ship? 0, because these are vectors, direction, matter. You don't just add the numbers, you add the numbers with the direction. Now, what if you had one over here pushing 1,000 units to the east, but you had have this sort of backwards here. You have another one on this side that this one doesn't see, pushing 2,000 units, a bigger tugboat, pushing that way. What's the net force? 1,000 to the east, 2,000 to the west, 1,000 to the west. This one's saying, what's going on here? You know, I'm pushing with all I got, and I'm getting pushed over. Okay. That's because there's a bigger force there. So that's what we mean by vector sum. Okay? That gives you the net force. Net meaning sum of those vectors, after you subtract anything else. I'll go give you a dumb sort of example of this. When we first moved into the house where we currently live, the previous owners had just let the trees grow wherever the trees wanted to grow. And it had quite a few trees, and we liked the trees. They were nice. But there were two really scrawny, scraggly pine trees trying to grow up through oak and pecan canopies, and they were enough light and they were trying to reach to the sun, they were ugly. And my wife said, I don't want those trees in my yard. We like trees, but those are just not in the right place. Well, my father-in-law came down with his chainsaw, and my brother-in-law, they lived in Huntsville, came down to help, and we threw a cord as high as we could to wrap around the branch of the tree. So Dan got on this side, I got on this side. Now, to get the most force, the maximum force, we should have pulled right next to each other, right? Me pulling this way and pulling on that side while Mr. Brazil cut the tree, because we didn't want it falling on other plants and things like this. We wanted it to fall. What was wrong with that picture?
It's gonna hit one of y'all.
Say again?
It hit one of y'all.
It would probably hit us both, you know, and we didn't want that to happen. So what we did, I pulled at this angle and he pulled at that angle. Now, we both were pulling, and we both wanted to pull at least as much as the other guy did, okay, because otherwise don't have trouble there. And part of the pull, there are two components to the pull. Remember, there was a same direction pull, but then there was an opposite direction pull, perpendicular to each other. This pull did no work on the tree. These two did. But that got the tree to fall in between us, and we were happy campers. So that's what we mean by some vector sum of forces. They're not always where you would expect them to be, but that's what you do. Have you ever noticed guy wires on power poles? If we, the Brazils had a place up on Smith Lake. Boy, to get up there in Winston County, you drive around like this, you know, a lot. And so the power pole would be here, one here. And every time there was a change of direction of the line, the power lines, because of the roads winding around, they had to have a guy wire. If they didn't, the wires don't pull the pole over. So the wires, so those are vector sums. You can bank on it. Those are vectors. The power lines pulling this way and pulling that way, so you had to have a guy wire over here to keep the pole upright. Those are all vector sums. That's what we mean by adding vectors. Now, they talk here just very briefly. I don't know. This is a good place to stop, don't you think? Okay. Because we need a little bit of a break. Because I've got to set up the lab, and I imagine y'all would like to get a little bit of moving around, maybe something to chew on or drink on or something like that. A little caffeine or something. So let's take a break now. We're going to try to be in the right down the hall in 253. Heading down this long hallway, first door on the right. Now, if there's a lab in there, if there's a class in there, we'll go somewhere else. But if that room's open, that's where we'll go for lab. Take a little bit of break now, but before you do, let me pass out the labs to you. You can't do much with them until we get down there, so that way you carry them and I don't have to. Okay, no, that's what it is. Okay. You get two? Don't be greedy. Okay. And by the way, this will be the longest lab all term. I'm sorry about that, but it is past 2, 1, past 2. 1 past 1. 1 past 2. And all right, take a little break. I've got to shut things down here, so it's going to take me probably a little bit more than 5 minutes, but I'm going to try to do it as fast as I can. Okay, I'm going to put this on pause. I'm going to get this a little more centrally located here so it will pick up my sound a little bit better. Okay. So what you got, if you notice the first bold word up there, what is a ratio? Yeah, something compared in a division sense. some number over some number. And that's what we're going to be dealing with most of this lab. In fact, almost the whole lab is dealing with that. The first, each team has 3 circles at your station. 2 of the teams have a big circle like this. Okay, one of you have a large cup, the top of that cup. All 3 teams have a circle like this. Okay, and all 3 teams have a small circle like that. Okay, now what you're to do, there's 4, 4, and 5 people at a station. Only have 3 circles, so spread around the fun, and you got lots of pieces of paper here. So get you a piece of paper and a pencil, and what you're going to do is, let me use one of these, okay? All right, don't lose your strings either, okay? Now, you're going to trace a circle on a piece of paper. Each person trace 1 circle. Then pass it around till another person traces that. And keep passing them around until you have 3 large circles drawn by 3 different people, 3 medium circles drawn by 3 different people, and 3 small circles drawn by 3 different people. You stop there once you've done this. I'll take this from y'all. I think I did. Okay? So, pass around until you have 3. You don't need 3 each, just 3 for the whole team. This is a lab. We're in teams.
I got a medium.
Okay?
I got the small one.
Dr. Fowler.
Yes.
You got it.
What's that?
The clear circles? Yeah, we do this.
Did I take it? Oh, you all stole their circle. Okay. Sorry about that. Okay. So everybody understand, the team only draws 3 large, 3 small, and 3 medium. That's all. Okay? Now once you've drawn them, okay. There's a medium. Going up in the medium. Each team should have 3 large, 3 small, and 3 medium. Stop drawing when you get those. Okay? What's that? Yeah, you got lots of paper. You can do whatever you want. Not each person, but each team. Once you got 3 large, 3 medium, 3 small, stop. Okay? Now.
So I need 3 of these.
No. Each team. 3 large, 3 small, and 3 medium. Okay? I see 2 smalls. I see lots of mediums. Oh, you got a small. Okay, got it. Look like I'll have. Now, every team has some meters, rulers. Okay? Now, what I want you to use is the centimeter side. Okay? Now, this one has a jagged centimeter side, so you have to measure, say, from 10 to whatever. So you measure your best guess of your small circle diameter, medium circle diameter, and large circle diameter. Okay? What you do now, if you'll turn back to page near the end, there's lots of pages. This is the longest lab we'll have all term. If you go to page 23, you'll see the circle data sheet. Okay? The small circle, you put down your best guess of the diameter of your 3 small circles. 3 different people taking the measurement and put it in centimeters, what you think the diameter of that small circle is. Your best guess. Small circle. And each one of you that has a medium circle, write down those diameters. And each one of you that has a large circle, write down its diameter. Okay, use the centimeter side. Oh, that's all right, but you can start with 10. You don't have to start at 0. Okay. Okay. So you put your diameters in there in centimeters. Remember, units are important, folks. All right. Do your best guess of a diameter. The diameter is the largest length you can get across the circle. You go too near the top, it's going to be too short. The largest length you can get across that circle. Okay? Okay. Do 3. And y'all are sharing data. You're on a team, right? So you write down what your diameters are. 1, 2, and 3.
4, 9. You get 4 on the centimeters. 5 and a half. This is the shear.
All right. Everybody got your. Okay. And hey, don't expect all to have the same numbers, even though you had the same thing. There are experimental differences. Live with your differences. They don't all have to be the same. Do your best guess. Best measurement. Okay, and everybody record the 3 small diameters, 3 medium diameters, and 3 large diameters on page 23, top of the page. You only need 3 large ones. Okay. You're sharing data. You're not all competing with each other. Yeah. Okay.
So can we put the same thing for each three then?
Okay. Okay. 3 different measurements. Now, 2 of them may be the same, all 3 may be the same. The odds are they're not going to be exactly the same. So write down what they don't. You don't expect them to be the same.
So who got 3 of them? You got 3?
No. Okay. There should be one person should have one small. Yes. Yeah. You're sharing data. You're one team. You're one rep.
I write my own also, right?
No. You write yours, share it with the others, you get theirs from them, you know. Diameter goes across the top. 1, 2, and 3. Medium, 1, 2, 3. Large, 1, 2, 3. Okay. Everybody's got those recorded. Those are in centimeters, right? Good. Okay. All the way across. Okay. They all should be relatively close, but they don't necessarily have to be the same. Okay? All right. Now, the next issue is a little harder to do practically, but let me get everybody down. It doesn't matter. It's longest dimension. They won't necessarily all be the same. Okay. I want to let this thing catch up. So y'all got your 9 measurements, right? All relatively close, but not necessarily the same, right? Okay. Y'all fairly close, but not necessarily the same. Oh, I like this. Decimals, good. Okay. Now, this one, I bet you'll have more variation on this. That's fine. Okay. You don't need but 3 for the whole team. If you got 3 small for the whole team, you got it. You got them all? Okay. Share, make sure everybody got it. Okay, now this next part is almost more art than science. Okay? Here's what you got to do. You got 3 streams at each station. This one I only see 2. Someone have another stream? Yeah, all right, got one. Okay. What you do is wrap the string around your circle. What you're getting is the circumference. And this is very hard to do well. Okay? Get it around the bottom as tight as you can without crawling up it. Okay? And then somehow hold those in place and lengthen it out to a straight line and measure the circumference. That's not easy to do. Use your rulers, and on the big one you might actually need the meter stick. No, you're going to do it, not me. Okay? All right. I know for y'all who have, this is really hard because it tries to crawl up the edge there. Okay? And you'll almost certainly need the meter stick. Be sure you use the meter side, not the inside. Okay. So, well, yeah, if your little sticks will work, that'll be fine, but the big one will probably be the bigger one. Yeah, in centimeters. Be sure you're still in centimeter mode. It's not easy, is it? It is easy to leave it down on the page. And y'all can help each other too. If you need someone else to hold the other end, get as many fingers in the pot as you need.
Let me just bring this one around to you.
If you try to pull too tightly, Carl, you get a nice loose. And almost certainly y'all will need the meter stick for that. So you need to make 3 measurements here. 3 measurements of the small, 3 of the large, and 3 of the medium. Try to do different people doing them so you get various experimental errors. While y'all are doing that, I'll set up for the next.
What'd you get for the small?
We're going to derive the formula, we're not going to use the formula.
That sounds like a calculation.
No cutting corners here, especially on circles.
Well, it worked.
Mr. Fallon,
Yeah.
so I think it's because that I thought we were going to move the time up, but then I think they said it just needed because we had too many students couldn't come.
Yeah, 3 of them can't come until 3:15.
So, I'm not overnight now, I have to be working.
They're what?
I'm not overnight now, I have to be working. I have like 30
Uh-huh.
So,
Okay. Well, be sure you got your data sheet and get your data from somebody. I'm certain they will be taking it home with them.
okay.
Your Liz Brooks.
Where should we get on the big 44.8?
Yeah, 32. Yeah, over here we got 13, 12, 13.
Oh, you doing that? What'd you get on the medium? So one more person. Did you do the medium? No, I did the small. I did the medium. I got like 13, but like, I'm sure I got. She got 13, 3 next week. I'm sure I got mine 13. You did the small J?
That's what I got right now.
Oh, I did your medium. What'd you get on your medium?
13.
Okay, y'all measured all your diameters, I mean your circumferences? Okay, me, are you from the right?
28.
All right,
Oh, wait,
all relatively close. How are y'all doing on yours? Got them all? Ooh, look at this. Got them all? You're still working. Okay. Okay. Y'all fairly confident you're okay with these. I can start picking up your circles because you may need more room later. Excuse me. Thank you. I'm sure y'all are still awake. Okay. I got all your circles.
What? Oh, you're gonna do that? You one soul, 2 legs, 3 arms.
Got them all wrong.
Almost 13, the other was
Yeah, I got 13. Got it? I got the measurements before I got the string? Okay, good. Okay. Now, y'all got them all? Good deal. Okay, we got all the data. Now what you do is on the third line in your table, you do your ratio and be sure you put circumference, which is the second line, over diameter, which is the top line. That's the ratio. Do you have calculators? Does every team have a calculator? Oh, good. Everybody got a calculator. Okay, good. So you do the ratio of the circumference divided by diameter. And write it down. Let me see some of your first writings. You good? I think I can pick these up now. I might be able to pick up these. No, you'll need to do this.
It's crazy, just a slot number. That's a big deal. It's a ratio.
You think y'all are going to need some scratch paper or not? If you need it, I'll give it back to you. But if you've already got the data, I'm just trying to do this so you won't have as much clutter. Press paper. Now you actually might, if you do need it, let me know. I'll give you some of these back. Minimize clutter. Leave these back. Still gonna be in the line. Everybody got pretty much 9 calculations? Okay, then what you do is take those 9 ratios. They should all be fairly close to each other, right? Okay, add them together, divide by 9. And that goes in, what did I do with my piece? Oh, there it is. That goes in the average C divided by D. Under table 2.1. So add the 9 together, divide by 9. You've already done it? All right, what you get? 3.288. All right. All right. Okay. There you go. Yeah. How you did? They all came out 3.14. Did y'all remember that little lecture on pseudoscience? Messing with the data to fit what you wanted it to be? Oh, we didn't do that, did we? I'll just say, it smells a little fishy over here.
I got 3.16.
Okay. Everybody got it? Numbers are looking good. Okay. Now, what do you think the answer should have been?
3.14.
What is that? Pi. 3.14. So the difference in what your average was and 3.14, that's your experimental error. So you should have, I hope, 2 digits of precision. So 2 digits, subtract that from, or 3.14 from that, and that's your experimental error. Good deal. Okay. Now, the next part of the experiment, by the way, to go back to where we are, what you've just done is part A, circles and proportionality constants. You did 1 through 4 on page 115. You're through with page 15, and now turn to page 16. Area and volume ratio. Okay? Now, all of you have 3 boxes with cubes in them. They're different looking cubes, but they should be all the same size. This is yours behind you here. I can move it over there if you want to. That's yours behind you. I didn't want it. That's why I wanted to clear the clutter. Okay? These old boxes are not the sturdiest, so be gentle with them. Okay? Area and volume ratios. So what you do is pick one small cube, just one small cube. Okay? You can do this as a team. You don't need to do it individually. One small cube. And measure in centimeters the length, the width, and the height. This is on page, okay. The directions are on page 16, part B, area and volume ratios. And the data sheet is on page 23, same place you were putting them, on the bottom half of the page. So pick A, each team pick A block. Yeah. Just pick a block. One person pick a block from it. Okay. Measure the length, width. Okay.
We don't need all three.
You don't need. Well, no, you will need them before the end. I promise.
We need one thing on there.
Huh?
The copper on there.
No, you don't have to.
No, I'm saying 2.5.
Okay. Is that centimeters? Okay.
I can put my.
Now, if I were you, I would use that jacket piece somewhere else. We're measuring the light.
Oh.
You gave us.
So measure the area of one face and multiply it by, how many faces does that cube have? 6. Measure the area, that's the length times the width of one face, multiply those together, and then multiply that by 6, and that's your surface area of the small cube.
I thought they're all the same.
15 centimeters.
Okay, it's actually centimeters squared. Okay, yeah. What is it? 2.5 times 2.5 times 2.5. Okay.
Medium cube bar.
All right.
Wait, are we just-
Now, what?
Do we times it by 6 or do we times
Oh yeah,
it by
yeah. I'm sorry. 15 times. Oh wait. 2.5. 2.5 times 2.5 times 6. Yeah.
Oh.
2.5 times 2.5 times 6.
It should be
37.
2.5 times. So 37.5.
2.5 times 2.5.
Yeah, I got the
Right.
37.5.
That sounds fairly reasonable. I don't know.
Centimeter square.
Okay.
I got the
Is that right? 2.5 times 2.5.
Thank you.
6.25. Times. That sounds right. Okay, everybody got the small cube done.
Is it cube or square?
Okay, you do the length times width, that gives you an area.
Oh, no, we got the answer. We're trying to see. 36. We got the answer. We cube or square.
The area is square, and the volume will be cubed.
Okay.
So I don't see any numbers written down.
Oh, no, we were doing it right.
37.5.
Okay, so put them down on the small cube, surface area of the small cube. What do you get? Y'all got a
sitting at like
surface area of small cube.
Ah,
Centimeters squared if you want to put units. Okay, now what's the volume of that small cube? Length times width times height. So whatever that was it 2.5? 2.5 times 2.5 times 2.5.
We got something. 15.6.
6.25.
what was it again?
Okay, length times width times height.
15.
Yeah.
That's huge.
Yeah, that sounds good.
Hey, it's right here.
You got a volume?
Is it centimeters square?
Second, it'll be centimeters cubed now. Because length times length times length. Centimeters times centimeters times. Yeah, that sounds great. All right, now for your next cube, what you do is take 2 cubes by 2 cubes by 2 cubes. Now, yeah, you can do it there. Okay. You see the idea? Make you a cube of the 2 cubes in each dimension. Okay? Yeah, it'll be a total of 8 cubes. Okay? Did y'all get it? Pile, yeah, and then pile 4 more on top of that.
No, I'm talking about you just said the volume. Yeah, 15.625.
He likes the wood, huh?
Yep, I can see it.
Yeah, it's lighter. He's lazy. Okay, I can tell. Okay, measure the length
Oh,
times
Yeah,
width.
you just break
Do
it
the
down.
areas.
I'm telling
Then do the body.
7 cubed.
Got what we're doing now?
Well,
Yeah.
obviously it's going to be 5.
Length times width times height.
So the ceiling is 5.
That's the
It's
volume.
5.
Okay, it better be.
That's
That's what I'm saying. Hey, I'm just saying.
Okay, so now we just do the same thing for the medium one. Right?
Yeah.
So it's 5.5. How many sides? 2, 4, 6 sides. 5 times 5.
Yeah.
So you do
5 times 6.
25,
Right.
25.
Yes.
That's the
Alright.
safest.
And now the volume was just 5 times 10.
Lumber, what's crazy, because you got this little bit of lumber.
Five times five.
This is a good one. This is good to make your block with. This is
Hold that right there.
No, I took my math and so
Okay. Now you do build on that and you get 3 across, 3 across, 3 across.
I
really want to live something.
So I took it first.
I ain't got enough money for that.
Your son. I just got another math.
3 high.
Not too high.
He just it was
I'm telling you.
We get here 8 o'clock in the morning. We don't get out until 7:45.
Then we leave tonight, we gotta be at work.
See, I told you, you need all these hours. Okay. So you've done your 2s, you got those? Okay, then do 3 by 3 by 3.
You running out of wood quick?
Oh, you're gonna be out of wood really quick.
Careful spell.
I'll do a lot.
There we go.
You saw it as roots. Alright. Yeah.
That's gonna be
Okay.
7.5 times 7.5.
Oh, we ain't done yet.
Oh, we go.
We got to go for 3. No, they got here.
Alright, so now it's
Using all the,
times 15.
We using all that.
but like 2.
Oh, that's helpful.
7.7. 7.5 times 6.
15. I didn't miss it.
Oh, that might be the problem.
It's
Huh?
Now it's
My numbers might be off. Let's measure to make sure. Mathematically, it should be right.
7.5.
7.5. Okay, I think it. Okay. 6. So 337.5 centimeters squared.
337.
Alright.
Y'all are doing great.
The big one? 421.88. How are you supposed to do the ratio when you got centimeters cubed and centimeters squared?
We just gonna show her and pull it out.
we're trying to elevate it from centimeter squared.
We be on the
Okay,
there.
whichever way you go around. Let's go down, man.
Oh, well, I was home. We had ground to say.
You know what I'm told?
As our own media and they're not second.
Bro.
Inches or
It's brass.
something.
It's a
It's brass, it says it underneath the thing.
well, I don't know. I don't know.
Oh, you was on inch.
Look.
Oh, it is brass too. Yeah, we're Remember that guy? It's fun beer on the table.
I said both.
You did. But I just, because other ones would look like their elements. So I just thought it would be.
Oh, it has a conversion. For some reason, it's on this. It says 1 centimeter cube equals 1 centimeter squared, but it says 2 centimeters cube equals 1.5, 1.746.
Oh, you get some more back.
I said, I ain't go from 1 to like
1 to 1 is good. 2 to 1.
Yeah, I did 2 to 1.
Well, hey, I'm just saying, but we need to look up and I. Please relook at your.
Okay, I heard the heavy there.
Yeah. Numbers.
Was you looking for like leaders from Grams to second or something?
No, we're just doing something. The computer was smarter than what it needed to.
I had a good time. Let's go ahead.
Why are
Got
there
it
differences
from
in
8
these?
to 3 o'clock.
8 to 3, 3:15 to 8.
That's my last.
Yeah, they don't have to be like certain ones in there. It's awesome.
The ladies I've been in school, I think.
Because they're all
They come in at 8:30.
they were all different.
I ain't get out till 2.
In the morning.
No, 8
Oh,
in the morning.
you said you told me that. Like you get out at 2 in the morning?
I must enjoy that.
He like, oh, that might be fun.
There'd be nobody here.
Yeah.
Get all the time, the roof, take the keys.
Sorry, I left y'all probably too long. Everybody's got their surface areas and volumes of all three cubes, right? All right, have you done the ratios? Okay, the ratio of the area, which is the top line, by the volume, which is the second line. Sorry about that. Huh?
We just divided them.
You divide them, yeah. Ratio means area divided by volume. I'm sorry, I didn't mean to leave y'all that long without.
You go with that number divided by.
37.5.
When you're having the squared and
Okay, yeah. It'll come out centimeters to -1. But you don't need, yeah, so that's fine. Good deal. Let me, I'll run the rest and I'll be right back.
2.4 white. Centimeters.
To the fourth. Now we're going up 1 more.
Is that what he said? Oh. I think he said -1.
Yeah.
Negative first.
1.
I'll see if I can do it.
2. Look, I thought you convert them, but it's gonna be like a long thing to do. 0.79, 9.
Makes her quit liking you, Jay. Yeah.
What's that?
I don't think that's what they say.
It says, I don't like Jay. And then the time and law patience, the law squaring.
Other than the block.
You never.
You can hold a block, but you can't cut
I
one.
ain't gonna stick it a little bit.
Like, if you take a solid piece of metal, you can't cut one.
You want to listen to anything in class, get some sand, get some wood.
Sand and glass, we don't make.
Go get some styrofoam.
Yeah, styrofoam and boards of some material in there.
I can handle it. We'll just put it in a CNC machine. Have you ever noticed it? I'm sure I can do that. My brother used it all the time.
I can figure it out.
Yeah, if I had any problems, I'd call my brother. He's he's used that stuff. I call my brother. My brother's
All right, all of you got the ratios? Okay. Now I think we're through with part A and part B now, right? Okay, part C begins at the bottom of page 16 and then goes into 17, 18 for quite a ways. Now this will be a little different from what you've done before in the fact of this. Each team has one container. Okay? Y'all will be working together on this, and what you should do is get one that is readable, okay? And be sure you do the centimeter side. Now here's a problem with these. One side of these is slanted a little bit. So how you estimate the length of that side is sort of do the middle of the slant. Okay? And get it to the nearest tenth of a centimeter if you can get that. Okay? You do the length, the width, and the height. Okay? To the nearest tenth of a centimeter, you record that. This team, we record it, turn to the back table. Very back left. Yeah, that one right there. What page is that? 24? Okay, you are going to be number 3, because you got the big one. You're going to be, you put your measurements on the table at the end. That one, okay. You're going to be filling yours in number 2, because you got the medium. Okay, y'all got the basic. So you're going to fill yours in column 1. Okay? Okay, the length, width, and height. Okay. Okay.
So what did you say with the
Not what I wanted. I had 14.
Okay. Yeah. But don't do it at the bottom. Do it about, about midway up, because you see that side of the thumb. That way you get the average.
The width will be 4.1. We'll keep them all correct.
Y'all are doing excellently, by the way. I think you're doing this lab the best of any class I've ever had. I hope I didn't say it too soon. Okay.
Give it a while. Long road home. There should be traffic.
Long one get off over there. Then it's 20, what is that? 20.
How far you gotta go?
Hour and a half. I gotta go all the way to Gadsden.
He
Gadsden,
goes
wow.
Gadsden, Lincoln,
You're just Scottsboro. You're even further. Wow.
I can make it 2 hours and 15 minutes.
Make it an hour and a half.
Y'all have classes tomorrow?
We got work.
Yeah, you don't have to, but you'll be going to work. Early?
7 in the morning.
7. That will be. But then you work Saturday too?
I work Saturday.
7 o'clock? What time do you get off Friday?
Friday I get off at 5.
Well, you got time to sort of catch up sleep if you
Oh,
catch up.
right. I'll probably go to
No.
bed about 9 o'clock. Right after football.
Oh, okay.
You sleep when you got football, right? You sleep when you got football, right?
Y'all through the blocks, I can start taking those up.
Hey.
Is there different types of it?
Y'all have to take your time doing this. Y'all already got your measurements? Okay, right, okay. Everybody got the 3 dimensions. Sorry. I was putting up the next slide. Okay? Then where's my sheet? There we go. Once you get your 3 dimensions, then you multiply height times length times width times height. That gives you your calculated volume. Okay, everybody's done that already? Good. All right, now, we only have 2 scales to share, okay? And take your container, and before you measure anything, be sure you zero the scale, okay? This looks like this.
Did you get 178?
135.
Zero the scale with this, okay? Be sure you zero your scale. Okay.
We want to empty it.
Here's our
Deal, thank you.
we organized it. Excellent.
Zero the scale and put it on and get the mass of the scale. Okay. Now, while y'all are doing that, I need to be doing the next part.
Heat for it. Heat, never mind.
I get 3 of them.
Okay. Yeah.
Oh, you have the 1, 2, 3.
Yes, that's
Oh, I know.
Very slowly.
He's $50.
Making see when they said, you got certain ones that make it miss. That makes 4 times.
I wish 59 was open. I could make it home in an hour and 15 minutes.
It's open.
Yeah. There's a scale up here. Y'all working on it? Okay. Did you zero the scale first?
How much you want in there? You trying to get home? Where?
Reading the scale. Okay, good. You registered the math and
Next I drive.
Okay. Now. Okay. Now, what you'll do next, did you fill it? Are you pretty sure that's full? I will try. Okay. Now, you look like you got yours pretty close to full. Okay.
Technically, you can put it over the limit.
What you gotta do.
Six together, start the stitches.
Say next.
Listen,
This is gone.
Yeah.
Just pour the whole report.
He got eagle eyes if we get her down. This guy.
Making this chair have something
Alright, what you gotta do next, very carefully, for this and that. That's just a big catcher for it. Okay. And then what we do, I thought I had the graduated cylinder somewhere here. Oh, I have
Somebody grabbed a couple juice out that thing right in the nose.
They look like they get that teeth from 10 pounds one day.
How do you guys graduate? I think I may have to do it.
Okay.
Oh,
I'm gonna try to get you a thing as soon as possible.
we use that to measure the volume.
Yeah.
One person there, don't think they're all like that. But they're probably are.
You said,
I went to a phone shop.
and I simply laughed.
He's from Pleasant Grove.
You're actually
I was at Pleasant Grove with you, and I'm like, right there.
He
Oh,
always says
it's something
Pleasant
that-
Grove.
It's a couple of places that link to
I would say
Y'all like what?
this is a bigger list. I mean, bigger list. You'll be safer pouring it in here. Then you'll pour into there because you can pour better. But yeah, catch it in here because that's the biggest. Yeah, it will, but you have less chance here.
No pressure.
Just water pressure. Hey, look at that, not a drop spill. Okay. Now hand the scale over to the so they can see that.
I don't think so.
No, you keep that. Okay. Now, pour that in here because this is easier to pour from.
That's how we used to waste salad.
Now, I think you may need both of these. Before I get
With
this
the girl with the
That's
bug.
what I'm saying. He mentioned different things like that back in time out.
Just crystals.
Farmer had a house outside. They were all Christian land. Did you own that?
You can measure it, but
People follow our farm. Ended up
you,
buying
okay.
it.
I'm afraid you're gonna do
And
that.
they went in there.
All right,
I still song and
Yeah, that's
Measure
the
volume of water.
stove.
This is what you poured out of this, okay? Let me get,
my experiences with that.
The Walmart guy.
Oh, God, that thing.
When you found
That-
out,
got a crack in
when
it.
you
I
was
thought it was
real
gonna
bad,
I even knew that one.
you don't want to go.
This thing got a crack
You
in
might
it.
get your hook.
yeah, they will. But I should have brought four of these.
They gonna steal my Jesus. They send me caps.
Hey, what I'm getting, they got LA. They don't want to carry
You
it.
know, bricks, if you stay in there too long, you know, bricks when you come out.
We're looking at, oh my word, I can't see that.
You full?
We're close. This thing's cracked on one end, so I'm trying not to kill the total up.
Yeah.
We're at 81.
What was without?
I don't think so.
We don't know.
Oh, we're going to
Yeah.
We're going to 50, 160, 180.
Yeah.
And that's.
That's what's the math of the container?
Oh, you didn't do the container?
What did you have as your math?
For the water back.
We'll have to take the. Make sure we get all the water.
So 181.
181 grams. Make sure we get all the water out of it.
Okay, let me go get
How y'all doing?
We forgot to get our master container. We're going to
Wait,
drive.
wait. What did he do with the water?
They poured it back out.
I'm pouring
Huh?
back into that.
Yeah, but you already have water in there. You should have emptied this first.
Oh.
Well, I knew it over again.
We got
Yeah,
that.
we gotta do it all over again. Sorry,
That's
I meant to be here watching you. I was watching another tape.
Number 4, and then around to water. Put up to
Just weigh that.
the rest of the bottom.
Okay. Y'all got your volume?
Is that right? 59 minutes. It's on the countdown now.
Yeah. To divide, yeah, to get this one, if you read on the thing, it says divide, calculate volume by the measured volume. That gives you an answer there.
Container with water should be 181. Try to get
Okay, wait. Oh, I will misread that. Okay. Then, let me see. Yeah, when you multiply them, you did get 356. I don't know, that's the thing.
I did one.
Oh, yeah, there's one, right?
That's all
But that's not the
right. Yeah. Yeah, master water by the
We put more water.
Okay. You got it?
Yes.
Okay.
191.
Yeah, wait just a second. Okay. Now, do that into here. Slowly, careful. Yeah, if you got the numbers and you're fine with them, they look like really good numbers.
Oh, 191.
I just need this for Bill. Okay. Now, for that water, slowly and carefully into here. And that's how you're going to measure your water. I'm on water. See a bartender in another life? Somebody's gonna be awful thirsty. Okay. Yeah, set it down. Okay. How are y'all doing? Are you all the way to the end? Okay. So your number one, you share your number one data. Okay, wait. Just a minute. Yeah. You're number 3, and they're number 2. What you get? Pretty good. Is that what you got?
We got 189, we have 198.
That's fine. That's still good. Okay, 189 here. Massive. Wait. Okay, wait. Here, you subtract first. This massive water is the difference between this and that. Right?
Oh, so we take the 10.5 off.
Yeah.
So it'll be 180.
179.
179.
Y'all did subtract. Yeah, well, we'll do a little bit of it. I'll
Either 180 or
191.
Hey, you're doing all the experiments.
180. 180.
or 180
And you do all the work.
Okay.
Water was 189.
And measure 189.
Alright. Then you do the ratios that they asked for. This one is the ratio of this to that. Yeah, this to that, and then this is the ratio of that to that.
With this water, are we done?
Or do it the other way around?
Alright, good. Now,
That's a shot right there.
one
think
thing
it was
that did come
The
up
measure volume
for
water is 180.5.
what y'all get for your weight?
What's the volume?
I got my number.
160, 67,
Oh, there's 191 here.
60.
So, okay, so we'll have 178.
And what you get on the
178.
Okay, that's a little short, I think, and then your height was the part. Okay, that's awful close to 3, it looks like to me. So that might be where you're off. So if you wanted to, it's not going to change any other measurement. If you want to, go back and you measure that again with a good ruler if you can find one and get those. Because those were the only things that throw them off of the. Not bad, but there's just a little
Calculated volume versus
Okay.
measured versus.
Everybody's got their container calculated. Oh, you're still working?
Still need to do the ratio. So what do you said
The one down here is this one divided by that.
194?
All we changed was
Then he said that bottom one was 189 divided by that.
No, this divided by that.
Okay.
Wait, this divided by that. Yes, this divided by that.
Yeah.
189
Divided by
195.
Anyone need y'all?
95. Actually, 0.965 makes it around 0.96.
Alright. We got 1.9.
Calculated volume divided by measured volume. Oh, yeah.
The measured volume, the mass of the water is bigger than the measured volume.
Yeah,
This is this one.
divided by the measured volume.
No. For the water.
To get it a little bit closer
That
to
one.
one.
Yeah, that's the mass of water. The mass of the water divided by the measured volume. That was it. I got 0.955.
Okay. Now,
0.9.
Okay, now the ratio of mass was just.
who has the best volume here?
I had to figure out the table. This is right.
I'm just gonna call this team one because they had measurement one. You're two and you're three. Okay? Y'all still calculating? Okay. Okay. For these two teams, 2 and 3, under your column 1, put down under 1, 8.5 centimeters. Your number 2, 4 centimeters. Your number 3, 3.2 centimeters. Okay? Jump down to number 5, 3 grams. Number 6, 109.5 grams. Okay? You do the rest of your calculations from that. Okay? Number 2. Who has the best writing? Not you. Okay. All right. Here. Number 2. Y'all ready for 2? 1 and 3. You ready for 2? Number 1, 14.5 centimeters. Number 2, 4.1 centimeters. Number 3, 3 centimeters. Number 5, 10.5 grams. Number 6, 191 grams. You can do your calculations from there. Okay? Who's got the best writing here? Not right. Not right. All right, number 3. Y'all listening up? Number 3. Number 1, 16.2 centimeters. Number 2, 8 centimeters. Number 3, 3 centimeters. Number 5, 30 grams. Number 6, 465 grams. And that's it. No, wait. Number 8, 430 milliliters. Did I give the others on you? Okay, I got to get that. Number 1, number 8 is 110 milliliters.
189.
Huh?
Ours is 189.
Okay. I don't want to get it too fast because of stuff. And number 2, number 8 is 189. Did y'all get it?
Yes.
Okay.
Hey, the first one.
I forgot this.
108.
Okay.
He calculated already. 108. For number 1. Hold on, for the mass of water, for number
7 is number 1.
Yeah. It'll be 100. Okay, and for the calculated volume for number 3 is 388.8.
Yeah, and then 0.97. Sorry. And then for what are you missing? Number 7 is 106.5. Number 7, 2 is 80. Yeah, I need everything. 435.
435.
We just calculate the ratio.
Volume.
I'm going to start hauling stuff down, but I'll be right back to answer your question to guide you the next way.
99.
Is that one?
Number 9.
Yep, number.
It's almost a $100. Makes me mad when I do that at the store. It's 99 cents.
$1.
Each of them calls for $1.
Number 7. We're going to do that.
Oh, yeah.
Number 7 for number 2 is 180.5.
We have
I don't have number 10 and number 2.
Well, yeah,
We have 0.9.
0.90 for the number 9.
I wonder who it is because it's bottom down. I think it might be. I'm sure it's from 80.5. You're dead in the wrong. 1.03. Oh no, I'll put it wrong.
Read the chapter. If I know, yeah, I'll read it. Yeah, and then you can have that equation sheet, so just because it's going to be built for.
No, man, we still got with, yeah, and we still got like that little sheet on the back.
I don't
We
know.
still haven't asked any questions.
I think this is just.
Gotta find this, chart right here.
I'm gonna draw like this one. Big old question. Mistakes that I'm sorry, I didn't see that.
You gotta get that thing like these.
Look at all these questions.
It's a lot of questions.
Why are you asking all
Just
the
the
questions?
results. I don't think it's
Oh man, we got calculus, graph, and your here.
Y'all got that pretty much finished?
Yes.
Okay. Now, y'all are doing great on time. Now, what you got to do next is on your graph paper, at the very back side. Okay? What you got to do, and by the way, the instructions are on page 18. It's make a graph, the top of the page, number 6. Okay, I'm still recording. Make a graph of the mass in grams, that's row 7 data, and the volume in milliliters, row 8 data, on the picture, to picture the mass per unit volume ratio found in step 5. Okay? Don't worry about that right now. Put the volume on the horizontal axis and the mass on the vertical axis. Now, let me just get an idea. What are your ranges of volumes? This is your
Calculated volume,
yeah, the row 8 data.
row 8
Row 8.
is anywhere from 430 milliliters to 110 milliliters.
Okay.
High and low.
Okay, 4, say again?
430,
2,
110.
110. Okay, give me your mass ratio rates.
Mass water,
Yeah.
mass water is 435 grams to 180.5 grams.
Those are a little bit bigger numbers or about the same? They're about the same, right?
Close, yes.
Okay. Either one of them bigger? Let's just go. Doesn't really matter that much. Let's put the volume horizontal here. Turn your page like this. Volume horizontal and your mass vertical. So, to get, what was the minimum that you had? 400?
minimum?
Yeah,
Oh, for which one? The volume?
either one.
No, the minimum is 110.
110?
Yeah.
Okay, 110. Okay, and what was the minimum mass and volume?
The minimum mass of water,
Yeah,
106.5.
okay. So both of those top 100. Okay, and so let's put that bottom line right here to be 100, 110, 100. Okay, wait. What's the maximum?
430.
430?
430.
Okay. Yeah, I think so. Okay. So basically, you can put your 0 at the bottom then. 0, 100, 200, 300, 400, 500. I don't think you're going to get any better than that. By what? 50s? Let's try it. Starting with 100 down here. 50, 200, 250, 300, 350, 400. Yeah. What's your maximum? 430. Hey, we can do that. Start the bottom here on the vertical scale will be 100. 100, right?
Yes.
Yeah. 100. Then 150 is the next dark line. 200, 250, 300, 350, 400, 450. Bottom will be 100 because you don't have anything below 100, right?
No.
Okay. You got that? Done this way. 100, 150, 200, 250, 300, 350, 400, 450. You got it. Okay? Now, on the horizontal, you got a lot more room. So why don't you just go and start with 0, 50, 100, 152, 253, 354, 450. That will go all the way across. Right? 0, 50, 100, 150, 200, 250, 300, 350, 400, 450. So you can start at 0 here.
Vertically, you got 8.
Vertically,
8 lines. And horizontally, you got 9. So 61 and a half.
Well, no, I mean, you got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, yeah. If you start with 0 here, then 50, 100, 152, 253, 354, 450. So you get right up to the side. Okay. All right, you got your scales, and you put volume on the bottom. That's in what? Milliliters?
Yes.
Okay. And your grams on the vertical scale, your mass in grams on the vertical scale. Okay. And then a point will be for your number 1. Find your volume along this way. It won't be far. It'll be 100 something, right? And now remember, you're starting at 100 on your vertical scale, so it's not going to be too far above that. Okay. So plot those points. You only got 3 points.
What are the numbers? 110. No.
But first one I just did this. I don't know. I just did. You don't matter. You know. So volume goes in bottom, mass is up there.
Yeah.
Okay, so what's the first volume? Number 1. We're looking at this volume of water. 110. So 110 is going to be right here. So
Oh, did I ever call? Yeah, I did
so
call.
is it 110? So what's the mass? 106. So I'm going to put it right there.
106. Yeah, 106.5. So 110.
Put it right there.
But so you started 110, then go where the thing is at? Yeah, you said 110. Then the water be 106. So start right here. You caught it 106. Go.
Okay, what's the bit?
I'm going to do the average.
What's the volume?
Like they go together.
So you call it 106 on that one?
189.
Because I was
180.
Yeah.
Right here, go.
Dr. Fowler.
Yes.
180, bingo.
You got a question?
We gotta go 180 now.
That's gonna be the mass. The volume is at.
We got
What is the volume? 189.
It's hot 180.9. If we were using those.
Or 189.
Yeah, the volume.
No.
180.
No. You plot this one versus that.
Like right here.
This is mass on vertical. This is, no, I'm sorry. Mass on vertical, volume on horizontal. This number is that.
So 3 of them, right?
Yeah. This is 1 point.
Oh, it's third.
110 and 106.
430.
110 horizontal, 106 vertical.
Volume is.
What was that? 406. You got that.
No.
430.
435.
Okay, I got 435.
Wait.
So what's the mass?
Wait. That's massive water, right? Yeah.
Yeah, mass water. Mass water. So mass is at 435.
105, 10.
Okay, so here all the way.
What's the volume?
The volume is 430.
430. 435.
Okay.
There's your graph.
106.
Okay. That you can do. Okay. Then.
You do 106, 430.
That's 430.
You don't have to write.
25 is right here. So
Okay.
30 right here on this line. Bingo, got it.
There you got a 3-point plot. All right. Get you a straight edge. Nice. Straight. Easy straight edge. And do. Don't connect the dot. Your fast straight line. Where'd you go? As close as you can, all 3 dots.
Benjamin Russell. Don't know again.
I'm perfect.
435.
You know,
You played there? You played there?
Y'all connect them. You draw the very fast straight line that is closest to all 3 dots.
So we just had people go play there. Play all
Very
the
straight line.
He's on famous,
Say again?
Yeah, he had
one of the celebrations like that. Popcorn.
Yeah, popcorn, cell phone.
Yeah, he had a cell phone in
The
the.
one in the data starting to do.
Above, below.
And he went back like 3 times, and then one time.
No.
Yeah.
Okay.
He like third all time and no, he like
Very,
second all time.
that's a pretty good,
First time.
pretty good. Okay.
Oh.
Anyone else through with your straight edge?
We saw your circle earlier.
Anyone else need a straight edge? Oh, you got it. Okay. What is it? Done.
Oh,
Good.
I was also good.
You know how
So
that
you were
is.
good.
Yeah.
All right. Now, what you do once you got your straight line, calculate the slope of that straight line. Pick a point near one end and a point near the other end that the
So I
line
got-
goes through, and then calculate the slope. Change the rise over run.
I got a question. I got
Yeah.
465.
110.
What's that?
465.
Oh, you did get a
435.
Under.
your math went to 455.
Pretty much the same one. Still off on the bottom.
Which thing is supposed to be?
Not that.
It's like that. 90
It's
is
gonna be a
right
positive-
here.
It's gonna be a positive slope.
45.
Don't find it, Rich.
Oh, I'm going to use something like that.
It'll be like so much over something, so it's fraction.
Like 15.
Oh, right. You're right. Oh, you're talking about that kind of stuff. We can have it. Y'all figure that out. Y'all have to figure stuff. Y'all have to figure that out. I'm here putting it down, man.
Draw your line and then put it on.
So you do rise over run. So run was 10.
This was on your
So it's 10 over 10, which is a 1
Yeah,
over
but you were
1.
here longer for the many terms.
So it's a positive.
I was saying, I was the one asking.
Yes, okay. For those who are ready to start with the questions, I was letting everybody catch up, but that's fine. Sounds like a dumb joke, but yeah. All right. For those who are ready to start answering questions, okay, when you do calculate the slope, you know how to do that?
Rise over
Rise over run. That's the change of mass over change of volume. take the 2 points as far apart as you can from each other on that straight line, and that'll give you a good estimate on that. So you write the slope in number 8 on page 18. Anyone got it yet?
Positive 1.
Say again?
Positive 1.
Whoa. Came right out at 1, huh? How many lines did you draw through that? No, I'm just kidding. Okay. Okay.
We just drew a line right through
And then put the points on place. Okay, good. Okay. All right. So it came out 1.00? Is that what you got, really?
It was 10 over 10.
10 over 10.
So
Okay. That's
there's
one.
down.
Yeah. Okay. Then your experimental error, 1.0 is your accepted value, so your experimental error is 0. Yes.
Oh, like it was 27 more for 30.
Okay, yeah, but get the closest straight line you can to all three points.
Completely off mark.
You drew the wrong line. It's like
That straight line you can.
so 10 over 10.
Yeah, you probably will. Yeah. Now, after you've gotten those points there, then calculate your experimental error. Your 1.0 is your accepted value. Oh, it's the change of your, okay. Let me see your graph. All right.
You think go
What you do, go right through that one, and right through that one. See your slope is rise over run. So basically, these two matches. Yeah. Okay.
Waffle House, baby.
This match my Waffle House.
You get Waffle House
Divided by
anytime.
this volume over that.
Waffle House.
Yeah, we want to have
There's a Huddle House around here.
7 and 8.
Oh, it's not even. It's not even.
Okay. Okay, y'all got put here again.
Oh no. Our Waffle House up here, but back home Waffle House ain't got nothing on it.
Well, I used a ruler to connect.
All the ones they ain't get food, so you have a good time.
All right.
I don't know. I forgot what it was.
Or she might not even know who you are.
Y'all got 1.0 on the notes, right? Wow, good.
Okay, we're lost again.
Okay.
How do we find it? Do we subtract?
Y'all be fine.
Right. That's the new number. Yeah, the large minus small divided by
We'll crown the way home.
the difference
You
between
gonna crown the way. Man, I hope this little money is gonna go back so fast. 3.5. No, it's
Oh, we don't even have our, we have to come back to this class next week. Mike would stay at home all week.
all right.
We don't have our automotive class. So we have to come back.
And the accepted value is 1 on the nose. You have the difference there is 0.02. That's 2%.
all right, you know, the gym over there.
So
This is a classroom with.
All right. Now, number 10 is something you probably could do on your own. This is on page 18. Density is defined as mass per unit volume or mass per volume. The slope of the straight line that you did was also a ratio. You did rise, which is mass, over run, which was volume, milliliters. So discuss why the volume data was placed on the horizontal axis and mass on vertical. So you could have the right units for density. So what you just calculated was your density. Now, once you've finished everything, you answer number 11 however you want to. But if you don't answer it, you're not getting any credit for it. Okay. So that's page 18. Hopefully everybody's done that. Now, your results. Number 1, I think from reading page 1, you probably can get what is a ratio. I say page 1, page 15. Okay?
15.
Huh? 19? No, page 15 is the you can get the pretty close to the definition of a ratio right there. Give several examples in everyday use. Y'all gave me some in class. Several people did. Okay? Number 2, how is the value of pi obtained?
Are we good?
By measuring the circles on the curves, the different circles.
Okay? What was the ratio that gave you pi? Or the sum team, the pi that gave you the ratio? Circumference divided by diameter. Okay? Why does it not have units? What's circumference measured in? It's an irrational number, but why does it have units? What was the units of your circumference? Centimeters. What was the units of your diameter? They cancel out. So it's a dimensionless quantity. Okay? Now, oh wait, I forgot something. Go back to page 16. I forgot this one. Go back to page 16. That's the one that you did after, that's the one where you did with little blocks, the cubes. Number 6 required you to give an answer. Okay? Anytime there's a lot of white space, you're expected to do an answer. Describe a pattern or generalization concerning the volume of a cube and its surface area concerning the volume of the cube and its surface area to volume ratio. So the volume, you're comparing the volume to the surface area to volume ratio. Now, where will you get that? That's your data from on page 23, the second table, table 2.2. What you're looking at there is the ratio, well, not the ratio, the comparison of volume to ratio, area to volume ratio. Okay? What happens as the volume increases, what is the ratio? It's what? The ratio of...
Volume increases, the ratio decreases.
Absolutely. That's what you put. Okay? All right. Now, that you got that one done, I know I'm doing these fast, but I want to cover as many as I can. Oh, okay. Okay. Okay, do I need to back up?
Yes.
What? Where?
To the beginning, I don't know what you mean. You work so fast.
Okay. Let's start with number on page 16.
I got number 6.
Oh, you got that one?
Yes.
Okay. So you've done that. Okay, that was
the only one that has to be done on page 16?
yeah, because that's the only big white space there.
Okay.
Okay. Now on 17, nothing to be done there.
Okay.
Number 18, number 8. You calculated the slope of your graph, right?
Yes.
Did you record it at number 8? You got number 8.
Yes.
Number 9, calculate your experimental ratio.
Got that.
You got that.
Yes.
Number 10.
No.
No. Okay. So density is defined as mass per unit volume, or mass divided by volume. The slope of a straight line is also a ratio, defined as rise over run, change in y value per change of x value. Discuss why the volume data was placed on the horizontal axis and the mass data on the vertical axis. Second, so you come up with the units for density. Rise is density, run is volume. Rise is mass, run is volume. Okay? Now, number 11 on page 18, I'd wait till I finished everything and come back and answer that. I'm not going to tell you how to, you answer it however you want to. Any answer you give will count fine, but if it's a blank, it doesn't count. Okay.
So, alright, page 19.
Page 19. The first question, what is a ratio?
The answer was on page 6.
Page 15, the first paragraph.
Okay. I'll get that.
Okay.
Two.
And, okay, number 2, how is the value of pi obtained?
I got that. So
You got that. Okay, number 3.
we get that.
What? Okay, we hadn't gotten there yet. But read that and tell me how different you think it is from number 6 on page 16. That's the same question. So basically, whatever you answered on number 6 on page 16, that's your answer for number 3 on page 19. Now, you okay with that? Okay. Now, everybody's still right. There we go on to number 4. Why does crushed ice melt faster than the same amount of ice? In a single block. Say again? More surface area. The surface area to volume ratio is much greater.
Say the mass versus.
What's that?
What ratio did you say the mass versus?
The surface area to the volume ratio. That's the one we've been
Surface
talking
area,
about.
alright,
Yeah.
okay.
Because you see, if you look at your data table, that same one we've been looking at of the blocks, when the
Because it's smaller, it's like how
the
bigger eraser, it takes
the small cube,
while lower eraser.
that's your crushed ice, has a much larger ratio of area to volume than your large cube, right?
Right.
Okay, that's why.
Yeah, you look at your surface area of your, the 6 we did versus the 3.
Okay. And almost the same thing, but kind of reversed, is number 5.
Which had more potatoes? 10 pounds or small or 10 pounds large?
10 pounds large has more skin.
Okay, now
I
remember,
think that's right. I was about to say 10 pounds, each one's gonna have more skin, so it's gonna have more.
your
more.
surface
yeah,
area
that's
to volume ratio is greater for the small potatoes, right? Notice the pounds. It's not 10 potatoes, it's 10 pounds of potatoes. It's going to be a lot of small potatoes in 10 pounds. That's a lot of skins. Okay, y'all got number 5 too then? Okay. And 6 is using your own words, explain the meaning of the slope of a straight line graph. Huh? What's this? I can't hear. Oh. Okay, y'all can take these home and work on them over the weekend.
No, we're gonna finish it out.
Okay. But the thing is, what I was going to say is, if we need to on Tuesday, we can finish it up. Any questions you have, we can work through those. You don't want to, you want to go and do it. Okay?
I'm not the class now. Everybody else can vote on this. That's just my opinion.
Okay.
I'd rather finish it up.
Yeah.
What's that?
I'd rather finish it up.
You would? Okay. All right. That's good. I was counting for y'all because I knew y'all had so long to drive. Okay. So, what's the meaning of a slope of a straight line graph? Rise over run. Okay. It's how much the vertical axis is changing compared to the horizontal axis. In other words, the ratio of vertical change to horizontal change. Rise over run. Delta y over delta x. You okay on number 7?
Densities calculated with.
What's that?
Densities calculated with mass and volume.
Yep, density of the units of mass per unit volume. So the units are right. By the way, you're the first lab I've ever had that finished this lab, all the measurements and calculations, within 2 hours. Y'all are great. Y'all moved along really well. Okay, this is the only lab with a whole bunch of problems too. So you ready to start the problems?
Yes.
Okay, aluminum block that is 1 meter by 2 meter by 3 meters has a mass of 1.62 times 10 to the 4th kilograms. By the way, that would be 16,200 kilograms. That's what 1.6 times 10, 62 times 10 to the 4th means. The following problems concern this same block. Okay? First, what is the volume of the block in cubic meters? Is what?
It should be 6 meters.
I can't hear.
6 meters.
6 cubic meters. 1 times 2 times 3. 6 cubic meters. Perfect. Now, same block. What are its dimensions in centimeters?
600.
No, the dimensions. The 1 meter height would be how many centimeters? 100 centimeters. The 2 meter depth, 200 centimeters. And the 3 meter length would be 300. So its dimensions in centimeters would be 100 by 200 by 300. But put centimeters after each one. 100 centimeters by 200 centimeters by 300 centimeters. See, these aren't that bad, are they? Now, it says, make a sketch of the aluminum block and show the area of each face in square centimeters. Square centimeters. So what I would do if I were you was do the very best job I could of copying that figure right here. Put it underneath it and see if you can trace it. Do a good job. Some people are good graphic people. Just do that same one, but rather than putting 1 meter, 2 meter, and 3 meter, put 100 meters, 200 meters, and 300 meters. Okay?
Is it centimeters or meters?
Okay, yeah, centimeters. I'm sorry, I said meters. 100 centimeters by 200 centimeters by 300 centimeters. Okay? But what they're asking for is the area of each face in square centimeters. So you see the top there? What would its area be? Okay, yep. No, it's 200 centimeters by 300 centimeters. So you have to multiply those two numbers together, right? The front face would be what? 100 meters by 300 meters. Multiply those two together, and that gives you square centimeters. I say meters, there's centimeters, centimeters. Okay. And then the face that they have dark colored, they say one face. What's its dimensions? In centimeters. Something right there.
BA 3 or BA 2.
100 by 200 centimeters. So that would be, multiply those two together, and that gives you square centimeters. So draw that, just show a dimension for each of those three faces. They've got a sister face on the other side, but just show it for each.
So the top is 600. Wait, would that be squared? Oh, that's for the whole thing. I got you.
You okay?
Length and width.
What's the mass of it?
That shows the area of each of those three faces. The area is
So you multiply this times 1,000.
So we're at 300 in here?
well,
Where are you at?
It's a kilo. So you got 1,620,000.
right there. So how many? 200 by 300. Okay, so multiply those two together.
That's what I need right there. Only 640,000.
I got you. I'm looking at you.
I want you to multiply 100 by 200. Multiply. Erase 100 by
How did
200.
you get that?
What's the rest for a moon?
100 by 200.
100.
20,000. Yeah.
Oh, okay. Do this.
No, he said it was
They're all square.
16,200.
I'm sorry.
That's what he said, was it was 16,200?
But you're supposed to identify the area of the faces. This face here is 100 centimeters by 300 centimeters. Multiply.
This is gonna be
This phase. Where you get 30,000?
The top one's gonna be 60.
Multiply 100 by 300.
So
100 by 300.
that'd be squared, right?
Yeah, I got
Ah!
I got 3,000.
You got 3,000. This is.
Oh, I ain't finished.
Oh, you haven't finished that, I see. Okay.
Squared or cubic?
That can be
Squared, okay.
Centimeter squared. Square centimeters, right. Square centimeter, square centimeter, square centimeter. Okay. Then the next one y'all have moved on to.
Yeah, you grant.
Number 4 is what the volume of the block expressed in cubic centimeters. And what did you get? Have you done that yet? Yeah. That's going to be a pretty big number. Oh, okay, I thought y'all were doing. Let me see you multiply width times length times height. I don't think so.
Three thousand times 2.
6 million.
313. Not 313 million. 3 with 13 zeros at it.
How'd you get that, dude?
Yeah, that's
Yeah. I did 30,000.
No.
No. That was that right. The base right there.
I'm sorry.
300
Slide me up to that.
100 times 200.
And then you multiply that by 100.
000.
It's too late to do with math. But mine is supposed to be
Something.
My mom asked her, you said something?
No.
Yes.
Multiply the 30,000 to 20,000.
No.
Yeah.
Oh, goodness,
I had it the first.
This is length times width times height, just like you did before. On every block you get. 100 times 200 times 3.
All these about we had the other one was at 115 signed 40.
100 times 200 times 300.
So 600,000.
I was like, why do you want to take this?
Okay, I want to see you multiply that out. 100 times 200 times 300.
I'm like, 6 million. I had 6
About 6
million.
million, exactly.
Nobody's gonna see me.
Yeah.
Oh, wow.
Number what? Number 7.
I haven't
Whoa.
overlooked since I did it.
Okay. What did you get there?
My last thing
About
to
4 you got.
Oh, this one.
Thank you, right?
Yeah, thank you.
Okay, number 5 you got.
16 million.
Okay. And then divide it. Okay, number 1. Question 6.
Density times.
You sit down.
We don't know. You can see my density, so that's why.
How did you number 5?
Huh?
How did you number 5?
Okay, the mass of the block is grams. Okay, turn back the page.
Oh, I see.
Yeah, there's the mass in
I missed
kilograms.
one. I missed one or
So
two.
you move your decimal 3 places. So in other words, increases the subtotal.
So we're ready for me.
That was
Grand.
1 point.
What did you get when you divided the mass?
No, I didn't get off that.
It's all with this.
What's that? Oh, yeah, okay, the mass, yeah, go back, flip the page.
Oh, no, it is 16.
16,
2.7.
Oh, good. 2.7 what? You just give me numbers, that doesn't tell me anything. Okay. What is this?
Now you grand.
Per?
What is this for?
That's it.
It's gonna be one, so it's gonna be 1, 2, 3, 5, 6, 7, 8, 5, 0.
1,600,000.
What you reckon that is?
6 million, right?
Not have your book in here, do you?
Divided by the.
One.
I got it in my bag.
Oh, get out of your bag.
16,200,000. I'm gonna show you. Look, you put it in your calculator.
First chapter we're in.
It says 1.2 times 10
That's the room before this. Just like this. Ooh, what's that? Look at that. What's that? What is that?
Next to
No, all
What
right,
is
take the 16.
Density of aluminum. The units tell you that's the density, and you're dealing with aluminum, and that was exactly right.
So that's your
top of which you like.
Yep. You want something what?
7 years cube.
Gram per cubic centimeter. What's that a measure of? What is measured in grams per cubic centimeter?
What?
Mass per unit volume. What measures that? Density, perfect. Okay. What's number 7? I think we just answered it. Yes. All right. My goodness, have we finished the whole lab?
Yep.
Amazing. Did anyone have any questions? You got them? My word. This is a new indoor record. Okay.
Right on time.
I gotta make sure I answer all the questions.
We actually 3 minutes early. But guess what? There's no refund, surely.
2.7 grams for.
Good deal. Thank you. Thank you.
Here's your eraser back. Thank you.
Oh, thank you so much for returning it. All right, good deal. Excellent, thank you. Goodness, I got so much to grade this weekend. Thank you so much for giving me so much grade.
You just try to 100 on the front, all of them be done.
That wouldn't be fair, would it? That wouldn't show that I cared.
Oh, man.
You want me to care, don't you?
Sure do.
Did you ask about hectare?
Oh, I haven't. My
Oh,
parents
that's all
are in. They're
That's
actually
all
down in Mexico right now.
Oh, really?
Yeah.
A lot warmer than it is here, isn't it?
Yeah, they took them a little vacation.
What's that?
They took them a little vacation. So
Oh, good
just
deal.
home alone for now.
You don't go home every day, do you?
No.
Okay, good.
We stay at Tannehill State Park.
Oh, I see. You got a camper or something?
All 3 of us stay together.
Oh, okay. Good deal. That's not too far, is it?
10 minutes.
Okay, thank you.
15 minutes, 10.
Yeah, about 8 miles. You could ride a little ride.
We'll see how that goes in the top of you next week.
Take your time, because I've got a lot of hauling to go downstairs. So there's no rush on my account. Good.
Now all I gotta do is study for the test. I kind of messed up, hoping I'm upset with it.
Messed up what?
With my staples.
That's all right. You keep them fully together. I'll keep them fully together. Thank you.
This is yours. That's yours.
Boy, by the end of the week, I'm just about had it.
We gotta realize I'll get up at 5. I work 7 to 3. I rush from work and get here by 3:15, and I'm here at 7. I'm beat.
Yeah.
That's every Tuesday and Thursday.
Wow. Yeah, I get up at 5:30.
Mm-hmm. I work right there at the wastewater treatment plant.
Oh, really? The one on 280?
Right here. That's
Oh, right here.
Water plant.
Oh,
Right the water tower.
Okay.
Back there by Splash Adventure.
Okay.
That's regular water, drinking water. I work with the bad water.
Oh, I see.
I work on some triple pumps and balloons and all of that.
Oh, I'm going to shut down the thing here.